Bhosle sir from Department of Physics, Sanjay Godawat University, Ategra, Kolhapur, Maharashtra. Next, I welcome Dr. Rajeshri M. Hudlur ma'am from Department of Physics, KLE Technological University, Hubli, Karnataka. I welcome you, ma'am, on behalf of BLD Association, SB Arts and KCP Science College, Vijayapur. I would like to extend our special welcome to another resource person, Dr. Rafiq Mullah sir, a postdoctoral researcher, Energy Safety Research Institute, Swansea University, United Kingdoms, who will be speaking later in the noon. I welcome you, sir, on behalf of BLD Associations, SB Arts and KCP Science College, Vijayapur. I welcome our Chief Patron, Dr. M.B. Patil, sir, President of BLD Association and also Honorable ex-Home Minister, Government of Karnataka. We welcome you, sir. I welcome our patron, Shri G.K. Patil, sir, General Secretary, BLD Association, Vijayapur. We welcome you, sir. I welcome Dr. K.G. Pujari, sir, Administrator of BLD Association, Vijayapur. We welcome you, sir. Now I welcome our beloved principal, Dr. A.S. Pujari, sir, to this webinar. We welcome you, sir. I welcome our vice principal and also IQAC coordinator, Dr. U.S. Pujari, sir, to this webinar. I'd also like to welcome our vice principal, Professor G.R. Ambli, sir, to this webinar. We welcome you, sir. I welcome our head of physics department, Professor C.N. Chowgle, sir, to this webinar. We welcome you, sir. And I welcome our coordinator of today's webinar, as well as the coordinator of Department of PG Studies in Physics, Dr. Girija Nimbar, ma'am. We welcome you, ma'am. I would like to conclude my welcome with warm welcome to all my colleagues and delegates to this webinar. Now, let us switch on our first session on social energy assisted purification of water using nanocrystalline. Now let us switch to our first session on social energy assisted purification of water using nanocrystalline stratified transition metal oxide semiconductor thin films, delivered by Dr. C.H. Bhosle from Department of Physics, Sanjay Godawat University, Kolhapur. I request Dr. Girija Nimbar ma'am, coordinator of Department of PG Studies in Physics, to introduce our resource person.
Good morning, everyone. Myself, Dr. Girija Nimbar, Department of Physics, SB Arts and KCP Science College, Vijayapur. I feel honored to introduce our today's resource person of session 1, Dr. Chandrakant Bhosle, Sir, Professor, Department of Physics, Sanjay Godawat University, Attigere, Kolhapur. Sir has completed Bachelor's to PhD in Shivaji University, Kolhapur. Sir has served as professor since 1992 to 2017 from Shivaji University, Kolhapur, and presently working as a professor in the Department of Physics, that is Sanjay Godawat University, Kolhapur. Sir has awarded by many national, international awards, and in 2018, Sir was honored by Dr. APJ Abdul Kalam Lifetime Award, and Sir has got many grants. I feel proud to say that in 2020, in Science and Technology, that is Volume 3 from Stanford University, USA, included Sir's name in the world ranking of top 2% Indian scientists. Sir has published 217 research papers in various national, international journals. Sir has guided 27 PhD students. I welcome you, sir, on behalf of BLD Association and SBR's KCP Science College, principal, vice principals, and staff. Thank you, sir.
Thank you, madam. Now I request Dr. C.H. Bosley, sir, to start the session. Sir, please.
गुगल मीट त्याला करेक्ट सर गुगल मीट मध्ये अनम्यूट करा रेड कलरचं बटन आहे ना खालती ते अनम्यूट करा गुगल मीटला जावा
हा ऐक
ओके ओके पुढं तिथं यायला लागलं का
एक बात कर बोलो
तुम्ही अनम्यूट करा सर अनम्यूट करा मग अनम्यूट करण्याचे आवाज येतो
अदर ना
Soumya Sajjan, madam, you have that option. Please, you only do it.
Okay, sir. Okay, ma'am. We will see about it. Okay.
Yes.
Unmute ಮಾಡಿವಿ unmute ಮಾಡಿವಿ
फर्स्ट वन जावा तिथं अनम्यूट करा तिथं आहे ना तुमचं रेड कलरचं खालती या थोडं तिथं बघा खालती या खालती सर तिथंच खालती त्या स्क्रीन मध्ये ते स्क्रीन सर ते स्क्रीन आहे ना ते स्क्रीन आहे ना खालती अरे ते क्लोज करा
हाँ 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 एक मिनिट इथं हाँ ओके हाँ यस थैंक यू हेलो एवरीवन हेलो
Good morning. Good morning, sir.
Good morning. Now, myself, Professor Bhosle, and I will be talking on solar energy assisted purification of water using nanocrystalline stratified transition metal oxide semiconductor thin films. Now, we all know that this fossil fuels, fossil fuel, they are buried under the surface of earth, and they consist of coal, oil, natural gas. And most of the countries, they are using these fossil fuels to great extent, and therefore, there is a fear in the minds of people that if the fossil fuels they are completely over, how to run this world. And therefore, according to my opinion, we should use we should use renewable energy sources to greatest extent. And we all know that solar, wind, ocean, geothermal, these are the renewable energy sources. And I am using here one of the renewable energy source, that is solar energy. And solar energy we have been receiving to the greatest extent on the surface of earth. And Indians, they are fortunate enough to receive this solar energy to the greatest extent. Now you see, so this is the campus of the Sanjay Godawat University, and the points which I am going to cover in this particular session, that is need of the water purification, why there is need of the water purification, and that water purification we are going to achieve with the help of the solar energy. So I will talk on the solar energy option, and then purification of water using oxide semiconductor thin films, and then acknowledgements. So, so this is the slide that is showing how the world population has been increasing with the year. So in the 1950, the world population was almost 3 billion. In 1990, world population increases to 4 billion. 1995, 6 billion. 2014, and this current year is 2020. So you can take this world population 7 billion. It has been uh, predicted that in 2050, 25, world population will touch to the 8 billion. So from this simple graph, simple slide, you will understand that world population is increasing tremendously, and therefore the demands of the people, they are also increasing tremendously. So let us now see how these drinking water resources get polluted due to the human activities. So this is the picture of the Godavari river, where the people they get bath, and how, to what extent the water is polluted, you can see over here. It is supposed that the people they see that sin is removed if we take the bath in the river, and therefore lot of people they are coming to Godavari river and they are taking the bath, and water gets polluted. Now this is another picture of the industrial sea, uh, this wastewater directly throwing into the river, and you can see to what extent the water has polluted. Here also, this industrial outlet mixing directly into the river, you can see these pipes. These wastewater is directly mixing into the bed of the river, and water gets polluted. See, everybody throws this garbage into the bed of the river, and therefore you see, after throwing this garbage into the bed of the river, to what extent the water may have uh, polluted. Now this nowadays we see every river contains this water plants. Now, water plants, they have grown up to the entire bed of the river. And therefore, because of this also, sunlight cannot reach to the water, and therefore water also gets purified. This is another problem of making the water impure. Dyes, they are discharged, and something around 50,000 tons of dye per year we are throwing into the water, and water gets purified. Water gets, see, 1 ton is equal to 1,000 kilogram. So 50,000 tons means how many kilograms of these dyes we are discharging into the water, that you can imagine. And to what extent the water might have polluted. This is the another problem. I will talk later on the dyes discharging. Now this boy is drinking wastewater, drainage water, and he doesn't know about the purified water, etc. But according to my opinion, we are also drinking to some extent the water like this only, and therefore a lot of diseases we face afterwards. So this is another problem of industrial area. See, because of the industry, lot of smoke is thrown into the atmosphere, and therefore we don't get the fresh air for breathing. And you see, this Holland is a country. Holland is a country where a lot of industrial area is there, and we don't get the fresh air for breathing in the Holland. Water is required to be cycled 7 to 8 times before we get that water for drinking. So development is a must, but we should keep the environment intact, and this approach is very necessary for everybody. Like this, we should remember it. And therefore, purification of water is of paramount importance. Now, water is indispensable source of our life. Now, water, what is potable water? So we should have potable water for drinking. In fact, it is our right to have potable water for drinking. Chemical free, metal free, bacteria free, mineralized purified water is called potable water. Now I would like to ask you one question. We are drinking water. So do you think that we are drinking potable water? So, see, please note that our survival, nobody is going to arrive here from nearby planet to kill us. In future, we may kill ourselves. And in order to protect ourselves, we should go for the solar energy option. Now, I will talk about the solar energy a little bit. So, it should meet the requirement of mankind years to come. Since I have been working in the physics department and working on the solar energy, my opinion is that solar energy will meet the requirements of mankind in years to come. Now, solar energy is inexhaustible source of energy because many years, thousands of years, we have been receiving the solar energy from the sun. It is replenishable source of energy. Replenishable means if the solar energy has decreased, nobody can go there and refill it. It is filling on its own. That is called replenishable source. It is also solar energy is non-pollutant source of energy. It doesn't create any kind of pollution. On the contrary, it minimizes the pollution occurred on the surface of Earth. So, solar energy is available all over the world freely and should be free from tax. Our finance minister cannot put any tax on the solar energy. See, important thing is that most of the energy demands in India can be met by simple solar systems, for example, solar photovoltaic modules, solar cooker, solar hot water system, solar dryer, etc. So if we use these devices, solar devices, our energy requirement we can meet through these solar energy devices. Now let us see. This is the picture of the sun. The positive point is that the earth receives solar energy 1.8 into 10 raised to 11 megawatt, which is several thousand times larger than the total world's energy consumption. This point we should remember. So how much energy we receive from the sun? That is 1.8 into 10 raised to 11 megawatt. And this energy is several thousand times larger than the total world's energy consumption. What is negative point? Negative point, solar energy is intermittent in nature. That means we cannot receive the solar energy during night time. And if anybody wants to use the solar energy during night time, he has to develop the storage system. That is negative points of the sun. See, energy received daily from the sun is 5 kilowatt hour per meter square, and this is almost equivalent to 4,300 kilocalorie per meter square. So if we have collector 1 meter by 1 meter, the area will be 1 meter square, and the energy received throughout the day will be 5 kilowatt hour per meter square. And this energy is sufficient to run all the appliances, all the devices in our house, for example, radio, TV, etc. So this energy is very important, solar energy. Now, if we again see the details of the solar energy, we receive the three types of radiations from the sun. Ultraviolet, the energy range is from 1.2 to 3.1, and wavelength range is 100 to 400. Visible region, wavelength range is 400 to 700 nanometer, and energy range is 3.1 to 1.7. Infrared, wavelength range 700 to 1000, and energy range is 1.7 to 1.9. So we receive the three types of rays: ultraviolet, visible, and infrared, and they are shown over here. So below this we have ultraviolet, this colored band that is visible, and this part is infrared. So this is very important. So solar energy can meet our energy requirement in years to come. Now, I would like to bring to your kind notice that you focus your attention on this figure. The energy received from the sun is 4.3 into 10 raised to 20 joule per hour, and the world requirement of energy is 4.1 into 10 raised to 20 joule per year. So this 4.3 into 10 raised to 20 joule and 4.1 into 10 raised to 20 joule, these figures, they are almost the same. Now where is difference? Difference is energy received per hour, and here world requirement per year. So whatever the energy that we receive from the sun in 1 hour, that is sufficient for the whole world for 1 year. So tremendous amount of energy we receive from the sun, and this energy is important for us. So we should keep on using energy. Now again, the important point regarding the water present on the earth. Now this is the picture of the water present on the earth. Let us suppose that the water that is present on the earth is 100% water. Now out of this 100% water, 97% water is saline water, and that is present in the sea. 1% is polar ice and glaciers. So if we add these two figures, 97 plus 1%, 98%, this 98% water present on the earth is of no use to the mankind. We cannot use this water for industrial purpose. We cannot use this water for drinking purpose. Now we left with, out of 100%, we left with 2% surface water. Now 2% surface water that is present in the rivers, that is present in the wells, and this water is very useful. But this 2% water which is very useful for us is also getting polluted because of the human activities. Now out of this 2%, 80% water is polluted due to the human activities, and it is estimated by the EPA. EPA is Environment Protection Agency, USA, World Health Organization, ICMR India, means Indian Council for Medical Research India, and NIRI India, National Environmental Engineering Research Institute India. All these are important institutions, and what they say is about 2 million human deaths per year occur due to the polluted water. So this is the death that is occurring per year because of the polluted water. Now out of these 2%, we use 70% water for agriculture, 20% water for industry, and 10% only water for private household. So we should keep in mind that water is very precious, and we should use this water very precautionally. So purification of water is of paramount importance, I will tell you. So our contribution to this water purification is that we have fabricated this purification reactor. We have fabricated, this is backside of the reactor, and here is one tube through which you can insert polluted water, and here is another tube through which you can get the purified water. And this is the 4 points where you can apply the bias to increase the purification rate. So let us see, this is backside of the reactor. Now we will see the front side. So this is the front side. You see, this is the front side, and this reactor is kept under sunlight. So when we insert the polluted water into this reactor, and when we take the water from this reactor, it is purified water. So simple is the process of purification of water. So if the sunlight is not available, you are performing the experiment during night time, then you can use this ultraviolet lamp. And using this ultraviolet lamp, you can purify the water during night time also. Now, how this process occurs? Let us see mechanism. So this is the reactor of one electrode, and this is second electrode, and in between them you have this polluted water, and the bias is applied, and at the same time ultraviolet radiations, they are allowed to incident on this water. Once you allow to incident the ultraviolet radiations, now you can have this deposited material is semiconducting material. So here we have valence band, here we have conduction band, and once this ultraviolet radiation they are absorbed, photon is absorbed. See, the electron is transported from valence band to conduction band, and this electron through external circuit, it arrives to the metal counter electrode, and this electron is captured by the oxygen, and you get oxygen reduction here. And here you have oxidation. So basic principle involved in the purification of water is oxidation reduction reactions. Now when the photon is absorbed in the TiO2 semiconductor film, electron and hole pairs generated. Some of the electron and holes, they recombine and the heat is produced. If this H plus ions, they combine with the H2O, H plus OH radical, they are produced. And this electron which is captured by oxygen, you can have oxygen radical. H plus plus D, that gives OX, this oxidation occurs, and OH radical plus this polluted particles, you get this deoxide. In this way, the water gets purified only using oxidation and reduction reactions in this particular manner. See, one reactor which I showed you, that is not sufficient to purify the water, and therefore we have constructed this 9-cell PEC reactor. 1, 2, 3, 4, 5, 6, 7, 8, and 9. So when the water flows from reactor 1 to reactor 2, 3, 4, 5, 6, 7, 8, 9, the water which is coming from this reactor is purified water. And this is a peristaltic pump, and that peristaltic pump circulates the water through this 9 reactor, and we get purified water. Let us now see. These are the solar cells to apply the potential difference to these 9-cell reactors, and we get the oxidation reduction reactions at very fast, and water gets purified. Now you will understand how this water gets purified using this simple idea. I will tell you, this is single reactor. Here is polluted water, and this polluted water through this pipe, through this peristaltic pump, it enters into the reactor. Solar energy at the same time incident on this reactor, and we get purified water. And you can apply the applied bias between working electrode and here counter electrode. Now let us see this process. This process, you will get purified water. You will understand. The reactor fills with the help of polluted water, and at the same time solar energy incident on it, and you get purified water over here. Let us now see. See, now this is the water. Now reactor is filled, and here we get purified water. So simple is the process. Nothing is difficult over there. So here at one electrode we have oxidation, at another electrode we have reduction, and we get purified water over here using this solar energy. So you will have to keep this reactor. You will have to keep this reactor on the top of your house, and you'll get the purified water. So active area of this reactor is 64 centimeters square, and we are using 9-cell reactor. Therefore, you multiply this area by the 9, you will get the total active area of the reactor. So we are getting purified water over here. Now, how this water gets purified? Let us suppose that we want to purify this oxalic acid. Oxalic acid is present in the water. And how to remove this oxalic acid present in the water? So let us see, when the photon is absorbed by the TiO2, it creates electron and hole pairs, and keeping this TiO2 intact. Some of the electron hole pairs, they recombine and get lost. Hydrogen and oxygen, when they combine, we get the OH radicals. They are also strong oxidizing agents. So this oxalic acid plus this OH radical, that gives OH minus plus COOH radical, and CO2 is liberated. Carbon dioxide is liberated at the TiO2 electrode. So this COOH radical plus this OH radical, we get H2O plus this CO2. H2O mix up into the reactor water, and CO2 is escaped. So OH radical and OH radical, that gives H2O2, and that H2O2 reacts with the 2H plus, and that gives O2 plus this 2H plus, and this H plus again react with the oxalic acid, we get COOH radical plus CO2. So in this particular working electrode of the TiO2, you will find that CO2 is escaped at the surface of the TiO2. At the counter electrode, what we observe that this electron is captured by the O2, and we get O2 minus and 2H plus O2 minus. These are combined and we get H2O. So at working electrode we get CO2, and at counter electrode we get H2O, and we get purified water. So this is so simple is the process over here. So at this electrode we get oxidation, at this electrode, backside electrode, we get reduction, and we get purified water over here. So this is the principle of working this. See, if you have colored water, here you will observe that how this color gets removed from the water. So at T is equal to 0, we started this reactor. At T is equal to 0, we started this reaction, and the color goes on decreasing, diminishing, and we get 0 color in 80 minutes. And we get very purified water in this reaction. So we have TiO2 electrode. This is the electrolyte. Illumination, we are illuminating by the sunlight. Flow rate is 12.2 liter per hour, and the applied reverse bias is 1.5 volt. So you can have this total reactions over here. So you see, if we have a dye, and this dye is suppose acid orange 7 dye, and if this acid orange 7 dye is circulated through our reactor, 9-cell reactor, and what you see that this is the color before circulating, and this is the color after circulating through 9-cell reactor for 80 minutes. So what we notice from this is that complete dye color is removed in 80 minutes. So this is the achievement of this reactor. See, at present there is no any device available from where you can remove the dyes from the water. And I told you in the beginning that 50,000 tons of dyes, they are discharged into the water by the industrial area, and therefore water gets polluted to the greatest extent. So this is very important. You can remove the dyes from the water using this reactor. We carried out another experiment. See, photocatalytic inactivation of E. coli bacteria using TiO2 thin films. So in the pure water, we deliberately added E. coli bacteria, and their number is 10 raised to 10 coliforming unit per ml. Per ml means 1 drop of the water. In 1 drop of the water, how many bacteria present? You can see how many bacteria present. They are 10 raised to 10. After half an hour, number of bacteria remain is 10 raised to 6 CFU coliforming unit per ml. Then again after half an hour, this number of bacteria, they become 10 raised to 3. Then again after half an hour, 10 raised to 2. Then after half an hour, just 80. And after half an hour, just 10 CFU per ml. So what we notice from these figures is that bacteria can be killed in this reactor, and you can have purified water using this reactor. So for the potable water, what we require is that pH should be pH should be 6.5 to 8.5 in this range. You know, normal water has pH 7. So mostly we require alkaline water. Mostly we require the alkaline water. The total dissolved salts, they are permissible to 500 mg per liter, and permissible quantity is 2000 milligram per liter. Manganese, if it is present in the water, you can have zero point 0.1 milligram per liter, and at the most you can have zero point 0.3 milligram per liter. Chlorides you can have in water 250 milligram per liter, and maximum chlorine that should be present, that is 1000 milligram per liter. Chlorides, they can be present up to 1 milligram per liter, and maximum quantity 1.5 milligram per liter. So if it is exceeded than this, then your teeth becomes brown, and bone, they are damaged. So fluorine is very dangerous in that way. Arsenic is also very dangerous. So permissible quantity is 0.05 milligram per liter, and if it is exceeded, then 0.05 milligram per liter, weight loss is there, depression or lack of energy is there, skin, nervous system toxicity is there. So arsenic in that way, it is very dangerous. Arsenic, it is very dangerous. Chromium is also maximum quantity required, that is 0.05 milligram per liter. Copper 0.05 milligram per liter, and it affects our kidney. Kidney gets damaged because of the excess of the copper in the water. Lead, if it is greater than 0.05 milligram per liter, then death can also be occur. So lead is very dangerous in that way. Mercury is still dangerous. If very small percentage of mercury is present in the water, 0.001 milligram per liter, then kidney is damaged, nervous system is damaged, and death may also occur if it is exceeding 0.001 milligram per liter. Coliforming bacteria. So I told you about this coliforming bacteria just now. So 10 coliforming bacteria in 100 ml, that they are permissible. Otherwise, gastrointestinal illness, gastrointestinal illness may occur, and that is also dangerous to mankind. So we should take care of while drinking the water. Water is very precious, and that water we should have. So this is the parameter. What should be the pH? What should be the color? What should be the odor? What should be the temperature, turbidity, total hardness of the water? What should be the percentage of calcium, chloride, sulfate, iron, nitrates? So all these factors, the coliform this bacteria, and here I have given this percentage, and this is before circulating the water, and this is the result after circulating the water, and this is the figures for potable water, and this water we should drink, where where this pH is 6.5 to 8.5. Water should be colorless, no color to the water. Then temperature should be 22. Then this turbidity should be 10 NTU, 300 hardness mg per liter, 75 calcium mg per liter, 150 sulfate mg per liter, zero point zero 0.01 iron mg per liter, and here you have this nitrates 45 mg per liter. You have total coliforming, that is less than 50, per 100 ml. So small, we should have bacteria in the water, and this is the coliforming bacteria. They should be less than 50 and per 100 ml. So these are the requirements, very critical requirements for the potable water, and this potable water is the most useful to drink. One should drink the potable water. Potable water. Potable water. We feel that whatever the water that we are drinking, that is potable water. But almost many diseases we face because of this unpotable water we drink throughout the day, throughout the month, throughout the year. See, this work which we have carried out regarding this potable water is with the help of Dr. Michael Newman Spellart from the France, and we have collaboration. He is our collaborator. Now, this work is supported by the Department of Science and Technology, DST, UGC. They have given a lot of funding to me, and these are our students, and they are actually working on this. Professor K.Y. Rajpure, who is in the Department of Physics, Shivaji University. Dr. A.V. Mohalkar, he is also assistant professor in the Department of Physics, Shivaji University, Kolhapur. Dr. Praveen Shinde, he is postdoc fellow in USA. Dr. Ulka Suryavanshi, she is a postdoc fellow in Germany. Dr. Devulkar is working in the Taiwan. Dr. Sambhaji Shinde and Dr. Mahadev Mahadik, both are in South Korea. And you see, many other students also, they have completed PhD and now they are working very nicely in the abroad countries. Dr. Yuvraj Hunge, he is a postdoc fellow now in the Germany. Earlier he was in the Pune University, but now he is in the Germany. So our students, they are doing extremely good job at their locations. So here, this is the photograph of Michael Newman Spellart with me, and you will surprised to note that he has been visiting to Shivaji University from 1999. So you can count almost 22 years. He has been visiting to Shivaji University and now Sanjay Ghodawat University without break. This is very important statement. Every year in the month of January, you will find Michael Newman Spellart on the campus of the Shivaji University and on the campus of the Sanjay Ghodawat University. Last 2 years, he has been visiting to Sanjay Ghodawat University also, and last 22 years, he has been visiting to the Shivaji University. So he is a very great scientist, and we Indians should learn from him how to work in the science. He is a very devoted scientist, I can say, devoted scientist, and he is devoted to the science work. Thank you very much. If you have any queries, you can ask me. Hello? Hello?
Yes, sir,
Hello,
we are
sir.
able to.
Soon we will forward the questions to you, sir.
Okay, okay,
Thank you,
okay,
sir. Thank you for the wonderful session.
okay, okay.
Sir, the questions are being sent to your WhatsApp, sir.
Okay,
So
okay,
please go through them, sir.
okay. Hello? Yeah, yeah, I will see. Okay, okay, okay. I will phone you after looking the questions. So, okay, okay, okay. Hello? Yeah, yeah, I am reading the questions. Okay. Immediately I will tell you. Hello?
So please continue, sir.
No, this these questions. Hello? Huh? Hello?
Yes, sir.
Now I am answering the questions.
Okay, sir. Fine, sir.
See, first question I am reading. I am reading the first question. Okay. Hello, can you listen me?
Yes, sir. You are audible, sir. You just answer the question, sir.
Uh, Now you
Okay.
see the first question, how can we stop the how we can stop the effluents, and we can make the strict law against, is there any rivers safe to drink the water? So no water is safe for drinking from any river because so many factors, as I explained. We should have pH, we should have bacteria present in the water, color, and pH. At least these things we should take into account while drinking the water. So, what potable water criteria I have given? Have you saved this presentation? Hello?
Yes, sir. It will be saved, sir.
Then you see the conditions for potable water,
Okay, sir.
and accordingly you can answer all these questions which you have given to me.
Okay.
See,
Actually, these are being posted on YouTube live channel by the delegates who are attending this, sir.
no, okay, but you send them that presentation.
Okay, sir. If you find anything which is different from your presentation, then you can answer them, sir.
Yeah, yeah. See, then it is difficult. See, for example, solar energy can be stored in 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 these days. In these days means where in the rainy season. It appears that from the question.
Yes, sir.
See, my observation is that, see, we Indians are very lucky to have tremendous amount of solar energy. Last year I had been to Canada. Hello.
Yes, sir. Yes, sir. You are audible, sir.
Uh, Last year I had been to Canada, where solar energy is available only for 1.5 months throughout the
Yes.
year.
Yes, sir.
And the people which are coming from the foreign countries to India, we call them as foreigners. They are having a lot of skin diseases.
Yes, sir.
They are facing a lot of skin diseases. We Indians are very lucky. We are getting solar energy almost 10 months without any failure.
Yes, sir. Yes, sir.
So we should make use of these solar energy by using many solar devices which I discussed.
Yes, sir.
Forget of this purification of water, that is not possible for the common man to construct that reactor and etc. But at least whatever the devices you are having in the market, for example, solar water heating system,
Yes, sir.
solar water heating system, you can have solar prototype modules. You can make use of these devices, and you can make use of the solar energy, and at least you can save this renewable energy. Using renewable energy, you can save this uh, uh, fossil coal, oil, natural gas. Coal,
Yes,
oil,
sir.
natural gas, they are very precious. And people from any country nowadays, they are using these fossil fuels to the greatest extent. And therefore, it has been predicted that
Yes, sir.
this oil and natural gas, they will be exhausted out in coming 30-40 years.
Yes, sir.
Now you see the vehicles running on the road, they require petrol or diesel or
Ye-
kerosene. You can imagine after 30-40 years how to run these vehicles, how to run
Yes.
the factories. See, and natural gas is the product which we get by from the natural oil. When we extract 1 barrel of oil, we get 170 meter cube gas. So if there is no oil, then there will be no natural gas. And in this way,
Yes.
very dangerous situation is going to come before us after 30-40 years. Coal can be lasted up to again 200 years. 200 years. Coal. Coal has no problem for us, but this
Yes.
oil and natural gas, they will be exhausted out in 30-40 years. So you send that my proposal to every participant who have registered and ask them to focus on potable water. Potable water is the water which we should drink daily, daily for our health.
Okay, sir.
Okay, okay.
Okay,
Now,
sir.
if anybody is having any specific question, these are very general questions.
Yes, sir.
And if any participant wants to ask me, discuss me, you give my mobile number to him.
Okay, sir.
Her.
Okay, sir.
They can ask me any question.
Okay, sir. Okay, sir.
Okay, okay. Thank you very much.
So thank you for the wonderful session, sir. It was
Thank
such
you.
an informative session, sir. Thank you,
Yeah,
sir.
yeah. Thank you. Thank you.
So now let us start our next session, which is on semiconductor nanostructure, colloidal synthesis, and their applications. This lecture will be delivered by Dr. Rajeshwari M. Hudlur, Madam, from Department of Physics, KLE Technological University, Hubli, Karnataka. We welcome you, ma'am, to this international webinar. I request Professor Amin Lane, sir, Head of English Department, to introduce our resource person, Dr. Rajeshwari Hudlur, ma'am. Sir, please.
Greetings to one and all. So myself Amin Lain, so HOD of Department of English. So it gives me immense pleasure to place all of your presence in the interest of entire institution. It gives me tremendous tranquility to be presenting the introduction speech of our esteemed resource person of this international webinar, Dr. Rajeshri M. Hudlur ma'am. So Dr. Rajshri M. Hudlur Madam, presently working as Assistant Professor in the Department of Physics, KLE Technological University, Hubli. She has completed her PhD from Okay. Uh, Greetings to one and all. So myself, Amin Line, HOD of Department of English. So it gives me immense warmth and great pleasure to grace all of your presence in the interest of all the entire institution. So it gives me tremendous tranquility to be presenting the introduction speech of our esteemed resource person of this international webinar, Dr. Rajshri M. Hudlur, Madam. So Dr. Rajshri M. Hudlur, Madam, presently working as Assistant Professor in the Department of Physics, KLE Technological University, Hubli. So she has completed her PhD from Karnataka University, Dharwad, under the guidance of Professor M.K. Rabinal, and her title for her research work was Synthesis and Optoelectronic Properties of Nanostructural Materials. So she was awarded with RFSMS fellowship to pursue her PhD. She has 10 publications to her credit in her peer-reviewed journals, including a review article. Today, Dr. Rajshri M. Hodlur, Madam, is going to speak on semiconductor, nanostructure, and colloidal synthesis and their applications. I ensure this international webinar will be profitable and fruitful for everyone. So, by saying this, I conclude. So, thank you, one and all.
Sir, can I share my screen?
Yes, ma'am. I request you to continue the session now.
I hope it is visible.
Yes, ma'am, it's visible.
Okay. Okay. So a very good morning to you all. First of all, I would like to thank the organizers. Just a second, ma'am. Shall I start, ma'am?
Yes, ma'am, you can, ma'am.
Okay.
You're audible, ma'am.
Okay. A very good morning to you all. First of all, I would like to thank the organizers for giving me an opportunity to be part of this webinar. The topic of my talk is semiconductor nanostructures, colloidal synthesis, and their applications. So the outline of my talk goes like this. I will briefly tell the historical perspectives of nanoscience and nanotechnology. What are the various types of nanomaterials? What are the important features of nanomaterials? And what are the various synthetic approaches, specifically the significance of colloidal synthesis in obtaining these nanostructures? This is followed
Excuse me,
by,
ma'am.
yes,
Excuse me, ma'am.
yes,
Can you switch on to the slide share, ma'am? It's in a window.
yes. Is it fine?
Hello? Okay, okay, okay.
Hello, is it fine?
Ma'am, now entire screen. You need to make it full screen, ma'am.
Yes, I have kept it in the full screen mode.
Now it's visible, ma'am.
Okay, okay.
Okay, thank you.
So the importance and the prerequisition of greener nanoscience, I will briefly discuss, and what are the various instrumentation techniques that are used to analyze these nanostructures. So at the end, a few slides, I will be discussing about what we have synthesized using what we have synthesized semiconductor nanostructures in our laboratory. Okay, so to start with the historical perspectives, the first ever concept of nanoscience and nanotechnology was presented by Richard Feynman in Caltech in the year 1959. Okay, so there he gave a talk, there's plenty of room at the bottom, where he speculated on the possibilities and potentiality of these nano-sized materials. So, however, if you see the roots of this emerging area, nanoscience and nanotechnology, goes very deeper than one might expect. They can be traced back in the ancient period. If you see here on the left side, there are some objects. These are ancient period objects. This shows the Lysagrus cup. This is the Damascus sword, the tainted glasses in churches. So if I consider in medieval times, the blades that were forged from the Damascus steel were highly praised for their exceptional strength and ability to remain ultra sharp. But little did these warriors know that these the Damascus steel was mainly coated by carbon nanotubes and cemented nano wires. So another example, if I consider, these are the colorful and decorative glasses. Actually, these glasses are reinforced with just 5 to 6% of metal nanocolloids, which makes them so beautiful and decorative. So similarly, unaware about the toxicity of lead sulfide colloids was mainly used for coloring of dyes. So in all these cases, these highly skilled craftsmen were unaware that they were using nanotechnology. So it's been with us from centuries, just waiting to be discovered. So if you see here, a main conceptual foundation of nanoscience and nanotechnology was laid by Richard Feynman in 1959. He gave a talk on there's plenty of room at the bottom, and he speculated the importance of these submicroscopic nanomaterials. So therefore, here and the term nanotechnology mainly was coined by Norio Taniguchi, and the invention of the scanning probe microscopy, the discovery of fullerenes by Kroto, Smollet, and Kerr, all these led to the discovery of this new emerging field, that is nanoscience and nanotechnology. So nanoscience mainly, we can define it as the study of atoms, molecules, and objects whose size mainly lies in the nanometer scale, that is 10 raised to minus 9 meters. And nanotechnology mainly deals with the technique of design, production of devices and systems by controlling the shape and size at the nanometer scale. So if you see here, nanotechnology is going to have a profound impact on our economy and society in the present century, and compared to the other technologies like semiconductor technology, information technology, etc. So we can say that nanotechnology will be the next industrial revolution. So this graph shows how nanoscience and nanotechnology are widely seen as having huge potential and will bring benefit to many areas of research and applications. And how it is attracting increasing investments from governments and businesses from various parts of the world. So one can say that these nanomaterials are widely used in consumer and industrial applications. So this flow chart shows the applications and various possibilities of nanotechnology, nanoscience and nanotechnology. It is being embraced by almost all the sectors of industry. So one can say that this is not just the future, it's already here among us. So with this brief introduction, the history of historical perspectives of nanoscience, I shall. What are these nanomaterials? So they are naturally occurring. They may be of human origin, like the cooking smoke, diesel exhaust, welding fumes, industrial effluents, sand blasting. But our interest mainly lies in the engineered nanomaterials, and they can be of different forms. They can be in the form of metal nanostructures, they can be in the form of quantum dots, magnetic nanostructures, nanocapsules, carbon-based materials, dendrimers, etc. So the rapid progress of these nanomaterials to dramatically change their properties at the nanoscale has opened up various possibilities of making new devices, instruments, and consumer goods to function in a much better way. So these are the various types of nanomaterials, and my focus, my further talk will be on mainly on the semiconductor nanostructures. With brief, when I'm discussing about the important features of these nanomaterials, a brief glimpse of metal nanostructures will be discussed. So what are the important features of these nanomaterials? What makes them so unique as compared to their bulk counterpart? So nanomaterials, as I told, any one of the dimension of the material, if it is in the nanometer scale, they come into the nanomaterial region. Okay. So the main important features of nanomaterials is they exhibit quantum confinement effect and the surface effect. So this figure shows the density of states for various dimensionalities. So I know in three-dimensional case, the energy levels are continuous, while in other low-dimensional structures, we see that it is discrete in nature. So this density of state is an important parameter which is mainly used to understand various optoelectronic and transport properties of the materials. So we already know that it is defined as the number of allowed state in a given energy range. So in order to understand the materials in low dimensional structure, we make use of the well-known Schrodinger equation, that is a particle in a one-dimensional potential well, to determine the allowed energy values and the energy wave functions. So quantum confinement, so using the density of states, how it varies in different cases, low dimensional structures, it may be the zero dimensional quantum dot, it may be the one dimensional nanotubes, it may be two dimensional films. In all these cases, the density of states becomes discrete in nature. And this equation shows how the density of states varies with the energy levels. So d, small d is the parameter which mainly describes the dimensionality. So quantum confinement effect, it is a widely used terminology in the study of mainly semiconductor. This quantum confinement effect, it is a widely used terminology in the study of semiconductor nanostructures. When we consider the bulk materials, the properties of the materials mainly is independent of the size and are mainly only chemical composition dependent. So because of the ability to tune their sizes, they exhibit some important phenomena. Like example, further in further slide, I will be showing because of their size dependent, how they exhibit some of the important phenomena like the surface plasmon resonance. Okay, so this is the quantum confinement effect, how the density of state, which is an important parameter in understanding the transport and the optoelectronic properties of various materials. So as an example, you can see here, whenever I consider a semiconductor, this is the energy with respect to the Bohr exciton radius. So this picture clearly depicts how the increase in the size of the particle will decrease the energy. So quantum confinement effect, due to the quantum confinement effect, when the materials go into the nanoscale region, they exhibit size dependent optoelectronic properties. So this table briefly depicts how the energy eigenvalues, the density of states for the bulk compared to the low dimensional structures is compared. So this is the density of states for semiconductors in case of bulk. If it is a two-dimensional layer, if it is a one-dimensional nanotube, or a zero-dimensional quantum dot. So this is how the degrees of freedom, the energy, allowed energy eigenvalues, the density of states, and the effective density of states can be calculated by knowing the nature of the material. So as an example, as I told you all, the important feature, one is the quantum size effect and another one is the surface effect. So as a simple example, I take a metal like gold. We know that gold in its bulk form has good conductivity, good thermal conductivity as well as electrical conductivity, very high melting point, and and uh, and they are good reflectors. But this material, when I get into the nanoscale region, their properties change with the change in their particle size. So you can see that this material in bulk form, which is noble, means it is highly non-reactive with acids, or now it has become more reactive, and hence you can see how by changing the particle size one can tune their optoelectronic properties. So one question that may arise is, what after tuning the size of these particles? So this, we know that metals are good reflectors, means they conduct heat as well as electricity, and whatever heat is radiations are incident on it, they are reflected back. If you take example of visible light or the infrared radiations, they conduct thermally, but here they show the surface plasmonic effect in the IR region. So here the one of the main advantages of tuning the particle size in the nanoscale is that they exhibit the surface plasmon resonance. It can be brought into the visible wavelength. So as an example, here if I consider gold colloids or the silver colloids, the main important phenomenon that these metal nanostructures exhibit is the surface plasmon resonance. So this mainly, it is defined as the process which takes place when there is coherent oscillation of conduction band electrons upon interaction with the electromagnetic field. And it mainly takes place only when the size of the nanoparticles is so small as comparable to the wavelength of the incident radiations. And this is mainly exhibited by metal nanoparticles. At the end of this talk, a brief 1 or 2 slides I'll be showing you all. Apart from these metal nanoparticles, there are other semiconductor metal oxide semiconductors which exhibit this important phenomenon, that is the surface plasmon resonance. So this is in general the uh, the the classification of nanomaterials, and our interest mainly lies in the semiconductor nanostructures. So quantum confinement effect, or it is the surface effect. Surface effect is mainly exhibited for all any class of nanomaterials you take. Surface, and if you see the quantum confinement effect, it is exhibited by the semiconductor nanostructures. So from here I'll start with the main topic, that is the semiconductor nanostructures. The earlier discussion was more generic. It was regarding the nanomaterials, what are the various types of nanomaterials and what is our interest. So to start with, what are these semiconductor nanostructures? So here, these semiconductor nanostructures, as you all know, semiconductors in their bulk counterpart, they like, take example of elemental silicon or germanium. They exhibit good absorption. Okay, so we know elemental semiconductors are silicon, germanium, and other compound semiconductors belonging to the fifth group, that is the third nitride, gallium phosphide. So these, and similarly we have semiconductors like belonging to the second sixth group and the fourth sixth group. So these are the various possible semiconductors. It may be elemental or it may be compound semiconductors in binary form, or it might be even in ternary form. So here mainly our focus is what happens to these bulk semiconductors when they are brought into the region scale, nanometer scale. So mainly they exhibit, the excitons mainly are confined in any one of the directions of space. They exhibit high quantum yield, they exhibit narrow and symmetric emission spectra, they are stable to photo bleaching, and their with the tunability of their size, they can be tuned to different colors from the range 400 to 400 nanometers. So as an example, this figure depicts how the change in size, this is an example of cadmium telluride nanoparticles. You can see here how its bulk band gap is around 1.7 electron volt, which appears here somewhere here. So by tuning the particle size, you can see how their optoelectronic properties can be used, can be tuned, and they can be used for various applications. So in order to determine the band gap, we mainly make use of the Bruce equation. This is the simplified equation, and once we know the effective mass of an electron and the hole for a particular semiconductor and its exciton Bohr exciton radius, one can determine the band gap. So this figure depicts various semiconductors and their particle size tunability and how their band gap can be tuned in a controlled way. So as an example, if I see here, take an example of indium antimonide. Its band gap is around 0.5 electron volt. So using once these materials, they are synthesized, they may be synthesized in the form of clusters, they can be synthesized in the form of films. Their particle size, once it is tuned, it can be tuned over a wide range of energy. So from 0.5 electron volt, it can be tuned up to 3.2 electron volt. So same thing applies for other semiconductor binary, compound semiconductors. So one can see here how these semiconductors, just by controlling the dimension of a semiconductor, which is smaller compared to the Bohr exciton radius, the band structure can be modified and it can be blue shifted to higher energy by the quantum confinement effect. So this clearly shows the quantum confinement effect that is observed in case of semiconductor nanostructures. We don't observe this in case of when the materials are in bulk form, because there the material does not depend upon, it is independent of the size. Okay, so my focus will be mainly on the synthesis, various synthesis approaches, specifically the colloidal synthesis. So there are large number of synthesis methods to obtain different types of nanomaterials, which may be in the form of colloids, it may be in the form of clusters, powders, tubes, rods, wires, films, etc. So these techniques are broadly classified into physical, chemical, biological, and hybrid methods, mainly to obtain various low dimensional structures. And these methods which are used depends upon the material of our interest and the type of the nanomaterial, namely 0-dimensional, 1-dimensional, or 2-dimensional. And it mainly depends upon the required size and shape and the quantity also. So again, these techniques, physical methods, chemical, biological, or the hybrid methods, again they are sub-classified into various ones. So my focus will be on the colloidal synthesis of nanostructures. So to obtain high quality nanocrystals with controllable physical and chemical properties, lot of efforts is being put, and a lot of efforts is being devoted to develop useful synthetic protocols to obtain high quality crystalline semiconductor nanostructures. The synthetic routes can be divided, we can broadly classify again this into wafer phase, solid phase and the liquid phase. Again, my interest will be with respect to the liquid. My talk will be mainly focused on the liquid phase approach. Again, these liquid phase approach, synthetic approach, it has proven to be an efficient route to achieve well-defined semiconductor nanostructures. And the semiconductor nanostructures which are synthesized by the liquid phase approach are also referred as the colloidal semiconductor nanostructures. And these nanostructures can be dispersed in suitable solvents. As I told you, this liquid phase approach, again further it is classified into aqueous and non-aqueous. They have their own advantages and disadvantages. Now if I consider the aqueous approach, mainly as the name itself suggests, it mainly uses water soluble precursors and water as the solvent. The synthesis is carried out under ambient conditions, and the yield and reproducibility is very high, and this can be extended to various class of binary ternary compounds. The main disadvantage of compared to aqueous approach, non-aqueous or the organometallic approach uses high boiling point solvents, and extremely dangerous reactants are used. And one more thing is, even though the crystallinity is very good, scalability is very poor, and reproducibility is minimal. So once we use this aqueous approach in obtaining the semiconductor nanostructures, we need to understand the surface modification, how the surface of the nanostructures, or it may be metals, it may be any nanocomposite, how the surface can be modified here. Hello. So the surface.
Yes, ma'am. You're audible, ma'am.
Okay. So the surface modification or the passivation layers, they act as insulators or barriers for the conduction of the charge. So capping or the passivation of surface is crucial in developing stable colloids. So these nanostructures, it may be metal, it is not only particularly applicable to semiconductor nanostructures, it can be extended to any nanocomposites or metal nanostructures. Okay, so the surface modification of these nanostructures play a crucial role, and they help in controlling the size and the growth of the nanostructures. So this figure clearly shows how an inorganic molecule, it may be a metal, it may be a semiconductor, how it is being capped organically. So these dangling bonds are the organic molecules, and they help in controlling the size and shape of this host material. So this is another form of capping. Surface modification can be done using inorganic molecules as well. So this is another example. Okay, so the liquid phase approach, basically it's a bottom-up approach. So in the previous slide I showed you, like whenever we go for the synthesis, it can be top-down approach or the bottom-up approach. So this liquid phase approach is basically a bottom-up approach, and the nucleation process is mainly controlled thermodynamically, and that can be understood using the Lemmer's diagram. So this figure shows how the colloidal synthesis process is carried out. Here we can see that we can vary the pH, you can vary the temperature, you can vary the molarity and concentration of the precursors. By controlling all these parameters, one can obtain various different sizes and shapes of nanomaterials. So the process of nucleation and growth of the nanomaterials can be well understood using this Lemmer's diagram. So this clearly depicts how initially, once the precursors are injected, how the nucleation process takes place, how clusters are formed, and with the rise in temperature and time, how cluster size can be varied, and after the nucleation, it is followed by the growth and further increase in the temperature or other parameters that will lead to post-fall ripening or the saturation state. So in order to understand, it is a more complex process, but still using the Lammer's diagram, one can understand how the nucleation and the growth process in nanomaterials takes place. So the nature of these engineered nanomaterials and their proposed uses, mainly they provide compelling results for the implementation, and because of that we need to implement greener nanoscience. So greener nanoscience, it is a prerequisite, because the end product they may find wide applications, but the process which we adopt may be of using hazardous chemicals or hazardous precursors. So in order to avoid these severities, we follow the greener nanoscience, which was developed by Paul Anates and John Werner. So in order to obtain nano-sized materials, we follow these 12 principles in order to protect our environment. So this green chemistry mainly is the utilization of set of these 12 principles that mainly reduce or eliminate the use of or the generation of hazardous substances in the design, manufacture and application of chemical products. And on the application of these principles, this will reduce the use of hazardous reagents and solvents, and that will improve the material and any energy efficiency of the chemical processes. And also it will enhance the design of the products. So by employing these principles towards nanoscience, that will facilitate the better production and processing of inherently safer nanomaterials and nanostructured devices. So in a very generic way, I will be just briefly discussing about what are the various characterization techniques that we make use of in order to understand the behavior of nanomaterials. So to characterize these nanomaterials are mainly characterized by various techniques. Although these techniques may be used, that are used mainly depend upon the type of the material and the information that one needs to know. Usually one is interested to know the crystallinity, the purity, morphology, thermal and the chemical state. So we make use of, in order to characterize these nanomaterials, we make use of various techniques like the diffraction techniques. In diffraction techniques, we have the neutron. I won't go in much detail about this. The ultimate purpose of using these characterization techniques is to understand the morphology, the crystal structure, the crystal size identification, and so on. So the diffraction techniques, mainly we have the neutron diffraction, you have the X-ray diffraction, then the dynamic light scattering technique, mainly to confirm its crystal structure and crystal size identification. It is mainly used for that. So this figure depicts, this is the powder X-ray diffraction, and using the Scherer formula, we can find out the particle size of the sample. Another characterization techniques which we commonly come across are the electron microscopy. So how do you confirm? We can't use ordinary optical microscopies to analyze nanomaterials. So we need to go for electron microscopy, which have resolution of up to 2 nanometers. So we make use of scanning electron microscopy, transmission electron microscopy, or you have the AFM, STM, and etc. Okay, so these mainly, using these electron microscopic techniques, they mainly yield the information such as the topography, the composition, then the composition and the crystallographic information, And the combination of this high magnification and large depth of focus, good resolution, and the ease of observation makes these electron microscopy one of the most widely used equipments. So apart from the diffraction techniques and the electron microscopic techniques, we also make use of spectroscopic techniques in order to observe the phenomenons like the quantum confinement effect. It might be, since we are using liquid phase synthetic routes, we introduce organic molecules, and using this technique, that is the FTIR, Fourier transform infrared spectroscopy, mainly it finds its great utility for identification of organic and organometallic molecules. So whenever we introduce organic molecules during the synthesis, the chemical bonding between, or the interface between the organic molecule, the surface modification of the nanoparticle by introduction of organic molecule can be analyzed using the FTIR spectroscopy. So another spectroscopic techniques we use is the UV visible absorption spectroscopy and the fluorescence. So mainly these clearly exhibit, here we mainly try to understand the electronic structure. The size dependent optoelectronic properties can be analyzed using these UV visible absorption spectroscopy and the photoluminescence spectroscopy. So these various, apart, there are many, but I have just covered few of them. Using these instrumentation techniques like the diffraction technique, it might be the microscopic techniques, or it might be the spectroscopic techniques. The ultimate purpose is to know the nature of the particles, its purity, crystal size. It might be the surface modification, the chemical binding using FTIR, and using these spectroscopic techniques, one can visualize the size dependent optoelectronic properties. So this is all about what are nanomaterials, what are the various possible nanomaterials. They may be naturally occurring, they may be engineered form. Our interest mainly lies in the metal nanostructures. And if you consider metal nanostructures as an example, we saw that they exhibit one of an important phenomenon, that is the surface plasmon resonance. And when I consider the semiconductor nanostructures, they exhibit quantum confinement effect. They also exhibit the surface effect. So by tuning the particle size, we are not only tuning their optoelectronic properties, their physical properties, their mechanical properties also are drastically changed. Like, take an example, its melting point is reduced. So for every particular semiconductor nanostructure, there is a specific critical particle size below which they exhibit quantum confinement effect and surface effect. So with this introduction, I shall now discuss about some of the nanomaterials that were synthesized in our lab. So I will be briefly discussing about the synthesis of zinc oxide nanoparticles. As I told you all, semiconductor nanostructures, there are various classes. They are elemental, they may be binary, they may be ternary. These all come in the range of low to medium band gaps. Another important class of semiconductors are the metal oxide semiconductors, and these are wide band gap semiconductors. Like, it may be the zinc oxide, it may be tin oxide, it may be cadmium oxide, or and so on. So here this figure shows the various possibilities, various shapes that can be obtained using various synthetic approaches. So you can see the zinc oxide nano ring, bow, rod, or you can see the tetrapods, etc. So various next to carbon, one can say that zinc oxide is considered to be one of the richest family of nanostructures. It can be tuned to different sizes and shapes. And the possibility is not only in physical methods, but also the tunability can be obtained using the liquid phase synthetic routes. So we shall see here what are the important properties of zinc oxide. So this is a metal oxide semiconductor with a band gap of wide band gap. It has a wide band gap of 3.37 electron volt, and mainly the three possible crystal structures of zinc oxide is the hexagonal root side, it is the cubic zinc blend, and the rock salt. Under ambient condition, one can obtain the hexagonal root site. But if you consider the cubic, the other two, these are obtained under very extreme conditions. Rock salt is almost like obtaining this crystal structure is practically not feasible under normal conditions. So the importance of this metal oxide semiconductors is that they are eco-friendly and inexpensive. They are luminescent materials, and it is an important functional oxide exhibiting near ultraviolet emission and transparent conductivity. So here if you see in this work, mainly our focus was to synthesize zinc oxide nanoparticles using thiols as the capping agent, and we studied how the dipole moment of these capping molecules changed the optoelectronic properties of zinc oxide nanomaterials. So as an example, here you can see we analyze using the X-ray diffraction. If you compare the uncapped, as I told you, these zinc oxide nanoparticles may mainly surface modified using these. We have adopted the aqueous route for synthesizing these zinc oxide nanoparticles, and various capping molecules were used to control the size of the particles. Like the thioglycolic acid, you have the thioglycerol and the mercaptoethanol. So this XRD pattern clearly reveals how the particle size can be tuned. So this is the uncapped, and by introducing thiols, you can see how the particle size can be tuned. And in order to see its morphology, we carried out SEM analysis, and we observed that the capping molecules mainly play a significant role in controlling not only the size but also the shape of the nanoparticles. So in order to confirm, as we know, the bulk band gap of zinc oxide is around 3.3 electron volt, and its corresponding wavelength lies around 375 nanometer. So clearly, when the UV absorption measurements were carried out, you can see the blue shift of the blue shift, and this clearly shows that the particle size is not only reduced, the band gap also increased significantly. So by capping these molecules, one can tune the size and shape of the particles, and what we observe from the UV visible absorption is that these particles shows clearly exhibited blue shift. That is the absorption peak is blue shifted, and clearly this was also observed in the photoluminescence spectra. So when we used acid-based thiols, they showed very weak fluorescence. But when we used ethanol-based along with the SH group, they showed prominent photoluminescence. They also exhibited high quantum yield. So using these thiol-capped zinc oxide nanoparticles, we mainly focused on how the dipole moment of these molecules can be tuned and how they help in tuning the optoelectronic properties. So you can see here, these are the various thiols, what is their respective dipole moment and the perpendicular dipole moment, and how the full width half maxima as observed in the photoluminescence spectra could be tuned here. Another example, semiconductor nanostructures that we were able to synthesize is the cadmium selenide quantum dots. So this cadmium selenide quantum dot, this cadmium selenide, this compound mainly belongs to the second, sixth group of the binary compounds, and its band gap is 1.74 electron volt, and it is a potential candidate in various areas. It might be since this band gap is close to that of elemental silicon, they find applications in solar cells, light emitting diodes, low cost thin film transistors, photocatalysis, bioimaging, etc. So here, mainly this cadmium selenide, it crystallizes into either hexagonal woodside or the cubic zinc blende structure. And the main important feature is that they exhibit very sharp and intense absorption, which is associated with narrow and symmetric emission. So using the liquid phase synthesis technique, that is the colloidal synthesis, as discussed earlier, we were able to tune the particle size of CDSC quantum dots. And the main advantage here, main advantage is that it was synthesized under ambient conditions, close to that is the boiling point of water, and we made use of organic molecules like the 3-mercaptopropionic acid for controlling the size and shape of the particles. So this approach, aqueous colloidal approach, is low cost, greener, and easily upscalable for synthesizing cadmium selenide quantum dots. And it is not only useful for this particular semiconductor, it is also helpful for, it can be extended for other metal selenide nanoparticles as well. So this figure shows the one batch synthesis. It was nearly in 250 ml, we could obtain nearly 3 grams. So large scale synthesis was possible using the aqueous liquid phase synthetic approach. So the diffraction X-ray, we carried out various characterization to confirm their crystallinity using the powder diffraction, and TM analysis mainly was carried out to confirm its crystallinity. So here you can see this is the TEM image of cadmium selenide quantum dot, and the scale that we have measured it in a scale of 2 nanometers. So here, even when the material goes into the nano region, the intrinsic property is still retained. So using the TEM transmission electron microscopy, we analyzed the crystalline property of cadmium selenide quantum dots. So here you can see how these quantum dots exhibited quantum confinement effect, and with the change in size, this clearly shows now the band gap of cadmium selenide is 1.74 electron volt. Its corresponding wavelength lies nearly to 600 nanometers. So this figure mainly shows how the particle size could be tuned, and we could clearly observe the blue shift. So the blue shift mainly shows that the particle size is reduced and therefore their band gap is increased. So this picture shows how the quantum dots appear under normal light and under UV light. So this is how they appear. So bulk CDSC appears red to reddish black in color, but we could tune it to different colors. So under normal light, this is how it appears, and under UV light, we observe high quantum yield with we observe highly fluorescent quantum dots with very high quantum yield. So here we performed, in order to understand the chemical reaction process, we first, since I told you all, we used 3-mercaptopropionic acid. So this, what was reported here is this 3-mercaptopropionic acid, which was used for controlling the size and shape of the particles, not only acts as a capping molecule, but also it acts as a reducing agent. So that was confirmed, and this work is published in Chemical Engineering Journal, where we attempted to to show that capping molecules like thiols, they not only act as stabilizing agent, but also they may act as the reducing agents. Okay, so this is all. I covered two types of semiconductor nanostructures, taking an example of zinc oxide and cadmium selenide quantum dots. Since I discussed about the liquid phase synthesis, briefly I would like to give a glimpse about using this liquid phase synthesis, we can obtain very high quality thin films. So one of the important special class of semiconductors are also the metal oxide, and zinc oxide also comes into this category. They are called as the transparent conducting oxides, and the various metal oxide that comes into these category are indium oxide. It may be tin doped or it may be fluorine doped. Then you have the zinc oxide, which is doped with aluminium. Then you have the gallium oxide and the tin oxide. Okay, so these transparent conducting oxides, here I am not dealing with this is not with respect to the nano regime, but since I discussed about the liquid phase growth, liquid phase growth can not only be used to obtain powders or clusters, it can be also used to obtain thin films. Okay, so transparent conducting oxides can be obtained using these liquid phase growth techniques. So these transparent conducting oxides, mainly they have wide band gaps in the range 3 to 3.5 electron volt. Then they have very high electrical conductivity, good optical transparency, and they are the main components of modern optoelectronic devices. So this figure shows how the conductivity, say the sheet resistance, so 500 ohms per square, which is used in touchscreen. The transparent conducting oxide with the sheet resistance of nearly 400 ohm per square meter is used in smart windows. So similarly, if you see the solar cell, the resistance, sheet resistance is around 1 ohm per square. Okay, so depending upon our interest and requirement, we can tune the sheet resistance or the electrical conductivity of these transparent conducting oxides. So here are some of the examples of metal oxide semiconductors. So in the further discussion, we see the liquid phase growth. So these are the various liquid phase approach which we use in obtaining these thin films. Here you have the chemical bond deposition, spin coating, dip coating, doctor blade, metering rod, slot casting, spray coating, screen printing, inkjet printing, aerosol jet, and so on. So these thin films are not necessarily obtained by liquid phase. Same as I discussed earlier, they are again can be obtained by different physical or chemical methods. My main focus further in this discussion will be on the spray pyrolysis technique, which is a very versatile liquid phase growth technique. So this is our home built setup, which we designed in our laboratory. So this is the atomizer, this is the heater, and we have not used the conventional spray approach. This is the heater here, and the glass slides fitted here. So you can observe that these atomizer with the precursor solution, and once it is sprayed on the preheated glass, one can obtain thin films of various types. So this is our home built setup, spray pyrolysis setup. And using this spray pyrolysis setup, we were able to obtain thin films of tin oxide. Here, why I am talking about this is, in the earlier slides, if you recall, I spoke about the surface plasmon resonance. We observed this phenomenon mainly in metal nanostructures, but in recent research work, lot of work is mainly dedicated to heavily doped metal oxide films. So here you can see that this is the tin oxide. Tin oxide, 1 to 10% of doping will yield us a highly transparent conducting metal oxide film, but on heavy doping, say from above 10%, 10 to nearly 40%, we added antimony. Still, the property of the tin oxide was retained even after the addition of 40% of antimony. So here clearly we can see that a sharp and visible range plasmonic behavior could be observed in heavily doped metal oxide films. So this mainly shows tin oxide which is heavily doped, and they exhibit surface plasmon resonance properties. So we studied the electrical properties of these films. So our interest was only mainly focused on the SPR properties, but in order to confirm their conductivity and their other electrical parameters like carrier concentration and mobility with respect to the doping concentration, we carried out the IV measurements, and using the Hall effect setup, we determined the carrier concentration and mobility of these thin films. So you can see here clearly with the increase in the doping concentration how the resistance can be tuned. Not only the resistance, even the carrier concentration and the mobility can be tuned using for these films. So apart from the tin oxide, now recent, as I told you all, a lot of work is mainly focused on metal oxide semiconductors, which are heavily doped since they exhibit plasmonic properties. So another important metal oxide is the cadmium oxide. So using our home built spray pyrolysis setup, we were able to make cadmium oxide thin films. So this cadmium oxide, in this TCO category, it was cadmium oxide which was first discovered by Carl Badekar. Its band gap is around 2.3 electron volt, and it crystallizes into cubic rock salt, and it possesses a very high carrier concentration, which is of the order of 10 raised to 18 to 10 raised to 20 electrons per centimeter cube in bulk form. And this cadmium oxide is referred as an archetypical or an ideal TCO because it exhibits impressive charge mobility of around 600 centimeters square per volt second and a very high electrical conductivity. So, in our laboratory, we were able to make thin films of cadmium oxide using the home-built spray pyrolysis technique, and various characterization techniques were used to confirm their crystallinity. And using, you can see here, using this liquid phase approach, that is the spray pyrolysis technique, we were able to not only tune the particle size, we were able to tune the electrical conductivity as well. So what we observed is, so this X-ray diffraction spectra mainly shows that it exhibits cubic phase centered phase of cadmium oxide, and the importance of this or the importance of spray pyrolysis is that especially for these metal oxides, it may be zinc oxide, it may be tin oxide or cadmium oxide, we observed no secondary phases or impurities were being observed. So here for this cadmium oxide films, by varying the pH, we could tune its particle size, we could tune its electrical conductivity. So using SEM analysis, the particle size and the cluster formation also could be tuned in a controllable manner. So the surface morphology and the grain size of the cadmium oxide films changed considerably as a function of the pH of the spray solution. So this is how, since cadmium oxide belongs to the TCO group, that is the transparent conducting oxide group, We studied its optoelectronic properties. So we can see here, just by varying the pH, even its absorption edge was slightly tuned here. And this shows that this graph transmittance spectra clearly shows that it is transparent, it acts as a transparent material in the visible region, that is above 500 nanometers. The electric with tuning, as we varied the pH of the spray solution. So our purpose was to tune the electrical conductivity of these films. So we also studied the IV measurements. We carried out the IV measurements, and clearly we observed that the by varying just the pH of these materials, we could control the electrical properties of these cadmium oxide thin films. So these metal semiconductor nanostructures, as discussed, it might be metal oxide semiconductors, it might be compound semiconductors. They find applications in various fields. So they are highly competent to the elemental semiconductors like silicon and germanium. And with this background, with this introduction of metal nanostructures, important properties of these nanomaterials, what makes them so unique as compared to their bulk counterpart, what is the significance of liquid phase growth. It is not that physical chemical methods or the hybrid techniques have disadvantages. All have their own advantages and disadvantages, but it is our interest. These liquid phase synthetic growths provide, it is low cost, its yield is very high. So and various nanostructures of shapes and sizes, of different shapes and sizes, can be obtained. And these are few examples I discussed. With this, I would like to end my talk. If you have any queries, you can put it in the chat box. Thank you very much. I would like to thank the participants for your attention. And once again, I would like to thank um, uh, SK Arts and SB Arts and KCP Science College Department of Physics for giving me an opportunity to be part of this webinar. I also thank Keli Technological University for their support and encouragement. Thank you one and all.
Thank you, ma'am.
If you have any queries, you can ask or put it in my WhatsApp group.
Hi, ma'am.
Yes.
Ma'am, there is one question I will
Yes.
tell you here.
Yes.
So that is, there is a question from Vaidiraj PK. That is, ma'am, whether it is possible to create wormhole through nanotechnology.
Ma'am, please repeat. Is it possible to?
Whether it is possible to create wormholes through nanotechnology.
What is wormholes? Can you put it in my WhatsApp?
Okay, ma'am. Just a minute. I will put it.
Yes.
ಬರ್ರಿ ಮ್ಯಾಮ್ ಜಲ್ದಿ ಮುಗೀತು. ಇದು ಕ್ವಶನ್ ಪುಟ್ ಮಾಡ್ರಿ ಒಂದು ಇಲ್ಲ ಅದ ನೋಡ್ರಿ ಕ್ವಶನ್ ಹಾಕ್ಯಾರ ಅದು ಹೇಳಿದ್ರೆ ಇದಾಗ ಮೇಡಮಿಗೆ ಅರ್ಥ ಆಗ್ತೈತೆ ಅದು ಇದಿದೆ ವೆದರ್ ಇಟ್ ಇಸ್ ಪಾಸಿಬಲ್ ಟು ಕ್ರಿಯೇಟ್ ವರ್ಮ್ ಹೋಲ್ಸ್ ಅಂದ್ರೆ ಏನದ ಅಂದ್ರೆ ಏನಂತ ಅವ್ರೆ
ವಾರ್ಮ್ ಹೋಲ್ಸ್
ಹ್ಮ್
ಇದು
ಹೇಳಿ ಮೇಡಮ್
madam.
Yes.
I think these wormholes are the one related with uh, time travel. I'm not sure.
Ma'am, can you put it in the WhatsApp group?
Ma'am, once again, I will ask the person once again.
Yes, yes.
And
if they have any queries, they can, once again, I repeat, if they have any queries, they can either mail me or put it in the chat box.
Okay, ma'am, we will provide it to them, ma'am.
Yes, yes, yes.
Mr. Vadiraj Kulkarni. Mr. Vadiraj Kulkarni, can we know what the wormhole means? Yes. Sorry, ma'am. He's not online, I think.
It's okay.
No, ma'am. He's on the way. What is wormhole, which has been mentioned in your question, sir? Mr. Vadiraj Kulkarni?
Can I stop sharing my screen, ma'am? I mean,
yes, ma'am,
the PPT.
Yes, sir. Ma'am, it's a Yes, ma'am. It's a quantum size.
Yes.
Which is connected to different time in space.
Different?
Which connects different time in space. So, I think it's related with time travel.
Okay. No, I have no much idea. Better you mail me the question. I will go through it and I'll reply back. Is it okay?
Ma'am. Okay, ma'am. Yes, ma'am.
Yes.
How many questions here? ಅದಕ್ಕಿಂತ ಮುಂಚೆಗಿನ questions ಆಗ್ಯಾವು. Where is it? Ma'am, one more question.
Yes.
What is percentage error in the graph where it is related with the semiconductor nanostructure slide, ma'am, where you represented a graph of band gap versus semi-metal?
Yes.
A person named Ashwajit is asking what is percentage error in this graph?
See, that error is negligible. We normally, there will be 5 to 7% of error and that is ignored. The main purpose is to tune the particle size. So once we tune the particle size, automatically the band gap also can be varied in a controllable manner. Okay. So the percentage error is normally 5 to 7%.
Okay, ma'am. Ma'am, the next question is from Azra Parveen. So what are the select criteria for TEM analysis grids? TEM analysis grids.
TEM analysis grids. No, it is related to what? TEM analysis grids means what? Grids of what? TEM, you are telling about TEM.
Yes, ma'am. TEM,
okay.
TEM.
It is
TEM
TEM
analysis.
TEM,
yes,
transmission.
Yes, ma'am.
So what you want from that?
Electron mic.
Yes, what you want?
The person is asking about selection criteria. What are the selection criteria for the TEM analysis?
Main thing, the name itself tells you transmission electron microscopy, the thickness of the film. Now we normally we put the nanoparticle suspension on a copper or a carbon coated copper thread. Okay, so it should be of not more than 100 nanometers. Means the film that is deposited or made on the grid, it should not exceed. So because the transmitted electrons gives us information regarding the morphology and the crystallinity of the material. So unlike SCM, there the thickness or the cluster size may be bigger, but here it should be below 200 to 250 nanometers. So the transmitted electrons gives us information regarding the imaging. I hope it is clear.
Okay, ma'am. Uh,
Thank you, ma'am.
Okay.
So, so myself, Shanaz Nadab, Department of Physics, SB Arts and KCP Science College, Vijayapur. I welcome all the dignitaries and resource person to this session, third session. Our today's third session is on thermoelectric effect. This lecture will be delivered by Dr. Rafiq Mullah sir, a postdoctoral researcher at Energy Safety Research Institute, Swansea University of UK. We welcome you, sir, to this international webinar. I request Ms. Vijayalakshmi, ma'am, Department of Physics, to introduce our resource person, Dr. Rafiq Mullah, sir. Please, ma'am.
A very good afternoon to all. I am Vijayalakshmi Karannava, Department of Physics in PG Studies, SB Arts and KCP Science College, Vijayapur. I feel very honored to introduce our today's webinar's resource person of session 3, Dr. Rafiq Mullah. He did his BSc from MGVC College, Mudedhar, and then he completed his masters in physics and obtained PhD from the Karnataka University Dharwad in the year 2018 on the topic development of low cost thermoelectric materials under the guidance of Professor M.K. Rabindranath. He later received a research fellowship from the Swansea University, United Kingdom, which is funded by the Welsh government to carry out research on thermoelectric materials. He is currently a postdoctoral working at the Energy Safety Research Institute of the Swansea University to develop cost-effective thermoelectric materials for heat through electricity and hydrogen generation applications. And he published around 15 papers in well-known journals. I welcome you on behalf of principal, vice principals, and staff of the BLDEA, SP Arts and KCP Science College, Vijayapur. Thank you.
Um, Thank you very much, madam, for the introduction.
Thank you, ma'am. Now I request Dr. Rafiq Mullah, sir, to continue the session. Please.
Thank you. Thank you for the nice introduction. And just give me a minute. I will share my screen. I hope my voice is clear. Can somebody confirm me back, please?
Yes, sir. Your voice is clear, sir.
It's
Thank
audible,
you.
sir.
Thank you, madam. Thank you. I don't know. I'm unable to share my screen.
Any problem?
It is not showing that PPT window to share. Only it is showing the one Google Meet page. I don't know what is the problem. Just give me a minute. Sorry about that.
No problem, sir.
Thank you. Shall I rejoin to check whether that works?
So just go to present now, open your PPT and
Okay.
click on a window or your entire screen.
Okay, madam. If I click my entire screen, I am getting okay.
ಇದು ಇನ್ನೊಂದು ಸೆಷನ್ ಐತಿ ಆಮೇಲೆ
Sorry for the delay. I hope my screen is on there. Excuse me.
Yes, sir.
Yes,
The
sir.
screen is visible, sir.
Okay, thank you. Thank you.
Okay.
I thank the organizers for inviting me to participate in this webinar. And I thank BLD Associations, SB Arts, and KCP Science College, Vijayapur, for giving me this opportunity. So I'll be presenting a basic topic. It is about thermoelectric effects, and I will try to cover what are the applications and challenges in this field, and some possible solutions to overcome those challenges. So outline of my talk will be it starts with giving a brief introduction about thermoelectric effects, such as the Seebeck effect and Peltier effect. Then the applications of these effects, known as the thermoelectric devices. So we will be discussing about thermoelectric devices and their working. And after that, we'll be looking at what are the applications of these thermoelectric devices in different fields. Then there are some challenges in thermoelectrics associated with the efficiency and materials, thermoelectric materials. We are briefly looking into that aspect. After that, the I have included the nanomaterial concept in the talk. We'll be seeing what nanomaterials will do to overcome such challenges. So I will conclude with finally I will conclude with some few Can you please confirm once again? My voice is, you are getting my voice right?
Yes, sir. Yes, sir. Yes,
Okay,
sir.
okay. Thank you, madam. Thank you, madam. So let us look one by one. In the Seebeck effect, Seebeck observed an interesting phenomenon in electrical conductors where an electric potential, generation of electric potential from a conductor when it is put under temperature gradient. So this is an electrical conductor, and this side is hot side, this side is cold side. When it is measured with some multimeter or voltmeter, it shows some voltage. So this was an interesting phenomenon which was first observed by Seebeck. So basically, the temperature gradient in a conductor produces an electric potential. So this produced electric potential is proportional to the applied temperature gradient, how much temperature gradient they are going to apply. So if there is more temperature gradient, I mean, if delta T is more, then delta V or voltage production is more. So this ratio is a kind of characteristic value for materials, and it will be kind of a standard value for each material, characteristic standard value for each material. That is the ratio of voltage and the gradient. So that is defined as a Seebeck coefficient, that is given by S is equal to delta V by delta T. So materials which produce better delta V under a given delta T are mostly suitable for this kind of applications. So when you apply temperature gradient, if you see sufficient amount of voltage, then that material is very useful to use as a energy generation device. We'll look how those devices work and all in the coming slides. So after this effect, after about 10 to 12 years, Peltier observed a reverse effect. Instead of applying temperature gradient, if we take a kind of circuit of two different conductors and apply some DC current or electric field, so by doing so, he observed that an electric current would produce heating or cooling at the junction of two different conductors. For example, this is conductor 1, this is conductor 2, there is a junction over here, and by applying current, we can see either cooling or heating effect in the junction between the two metals. So uh, this was completely reverse effect of Seebeck effect, where the temperature gradient was able to produce voltage, but here voltage can able to produce the temperature gradient. Temperature gradient means this is cold side, and these two ends will be hot sides. So heat will flow away from this junction because of this voltage, and due to that we get cooling effect on the junction. So this cooling effect is directly proportional to how much cooling one can achieve, is directly proportional to the Peltier coefficients of these materials, that is defined by the P is equal to dq by dt by I. Dq by dt is rate of heat flow for a given applied conductor, sorry, current. So materials which carry more heat away from the junction for an applied current are better suitable for such applications. So these two are kind of opposite effect. So in Seebeck effect, we are producing temperature gradient into potential. In Peltier effect, we are producing the potential difference into temperature gradient. So basically, these two thermoelectric effects, or the thermoelectric effect in general, refers to a phenomenon by which either a temperature difference creates an electric potential, that is known as Seebeck effect, or an electric potential creates a temperature difference, that is Peltier effect. So these two effects are opposite in nature, in fact. And the materials which show these thermoelectric effects are known as thermoelectric materials. So typically they are conductors Usually semiconductors are preferred for these applications because of the suitability of nature. Again, we'll see how they are suitable for the these thermoelectric applications. So now we know there are two effects, Seebeck effect and Peltier effect. So from the Seebeck effect, we can convert heat into electricity, and from the Peltier effect, we can convert electricity into either cooling. Of course, I should write heating. So you can cool, you can either choose to cool a junction, or depending on the direction of the current, you can heat that junction as well. So that decided by the direction of the current in the circuit. So electricity can be converted into cooling effect by Peltier effect, and in the Seebeck effect, heat can be converted into electricity, or temperature gradient can be converted into electricity. So based on this the properties, these properties, people have were able to produce two different devices. Of course, they working mechanism is same, but their function is different. So one is known as thermoelectric generator. It produces electricity from the heat. Another is thermoelectric cooler. So it acts as a cooler when you apply electric power to that device. So these are the two important applications of the thermoelectric effects, which are Seebeck and Peltier effects. So basically, I will try to focus on the working mechanism of thermoelectric generator, because I am working in that field. Of course, it is uh, slightly bit different for the cooler, but it will be very convenient to understand how thermoelectric materials work if we consider the concept of thermoelectric generator. So let us consider a conductor. This is a thermoelectric material which is connected to a multimeter or voltmeter under open. This is open circuit under open circuit condition. When we maintain the temperature gradient along the conductor, hot and cold junction, the charge carriers of the conductor are going to diffuse from hot side to cold side, and because it is open circuit, they are going to settle down here or accumulate on the cold side, cold junction, cold side. And because of that, if it is n type conductor, the negative charge carriers are going to diffuse from hot side to cold side, and they are going to accumulate on the cold side. Because of that, the cold side gets net negative charge, and the deficiency of electrons on the hot side ultimately creates a net positive charge. So it is a kind of potential difference, plus and minus. It is a kind of small battery producing some voltage, but it should be maintained under some temperature gradient. So we can see under a temperature gradient, conductor generates a small voltage. So this is a small a device, or one can say a thermoelectric generator, which can convert heat into electrical power. So this is the standard configuration that people use in the devices, thermoelectric generators. So they use one N-type conductor and one P-type conductor. They are connected like this. This is nothing but PN junction. So by shorting P and N materials and having this kind of arrangement, open circuit arrangement, we can see the when it is maintained under temperature gradient, the charge carriers, the majority charge carriers from the N side and majority charge carriers from the P side goes away from the hot side, and they are going to accumulate over here on the negative side of the conductor. For example, in N type, negative charge carriers are going to diffuse from hot side to cold side. Then this side becomes net negative charge, and because of this negative charge, this side becomes net positive charge. And similarly, in case of P type material, the positive charge carriers are going to diffuse from hot side to cold side. They are going to settle down here, and this uh, part becomes net positive charge, and because of this, net negative charge will be created here. So when we measure this potential difference between this and these two I mean, considering entire length of this device. Sorry. So we can see some voltage, and this voltage will be the sum of this voltage and sum of this voltage. So for example, if this conductor is producing a potential difference of 5 millivolts or voltage of 5 millivolts, and this is also producing a potential difference of 5 millivolts, then the voltage measured will be sum of this voltage and this voltage, and we see total 10 millivolts. So this is how thermoelectric generator works. It is like having two batteries in series. So we have this as a one type of battery. This is another type of battery, but ultimately they are connected in series. You can see the sign of their charge, negative, positive, and negative, positive. It is just like two batteries connected in series. So negative, positive, again negative and positive. So when we connect this kind of uh, uh, configuration, this when we have this kind of configuration of batteries, we are going to get the addition of the voltages of these two batteries, and we get more voltage. So this is the a kind of basic concept or standard configuration that people use in making thermoelectric devices. So let us look the commonly available thermoelectric generators uh, are shown here. These are small thermoelectric modules which can be used to generate electrical power, and inside these devices there are plenty of P and N materials connected in series, just like this figure. So N type and P type materials, and from one junction we get a small voltage, let us say 10 millivolts, but that 10 millivolts is not sufficient for any practical applications, and to make it higher voltage, one has to connect uh, multiple junctions, PN junctions, in series. So by connecting multiple PN junctions in series, we are going to add all the voltages from the PN junctions. So we are going to get voltage from this PN junction, voltage from this PN junction, voltage from this PN junction. So when they are in series, we know voltages in series are added up into and that produce into a big voltage or more large voltage. So all these junctions are maintained under temperature gradient, and when they are maintained under temperature gradient, they produce sufficient voltage for practical applications. So here, this surface, there are two surfaces in this device, top and bottom, and if you heat one surface and maintain another surface either cold or room temperature, that means you are maintaining temperature gradient across the device. So that means you are maintaining temperature gradient across the conductors, thermoelectric conductors, and because of that, the charge carriers in all the conductors diffuse from hot side to cold side, and all the voltages will be added together, and finally we get better voltage for any, and that can be used for any applications. So these are the two simple and basic figures which explain about the Peltier effect and Seebeck effect of thermoelectric generator. One is thermoelectric generator, another is thermoelectric cooler. In fact, both have same configuration, but only thing is in case of Peltier effect, we need to supply some voltage to get cooling effect. So why people choose two different conductors instead of same conductor? One can ask. If we use same conductor on both sides in this kind of connection, so the voltage produced by this one will be cancelled by voltage produced by this one. So to avoid that kind of cancellation of voltages, people prefer to use this kind of connection. By using this kind of connection, we can get addition of this voltage and addition of this voltage, and by repeating such junctions, we can get better voltage. So already we discussed this concept. Here, in the Peltier cooler, when we apply a DC current and depending on its direction, this can be either made as a cooling site or a hot site. So that is decided by the direction of the DC current. So for example, in this circuit, now we have the positive side of the battery is connected to the N-type conductor, and negative side of the battery is connected to the P-type conductor. The majority charge carriers in the N-type are dragged towards this side, and in the P-type, the majority carriers are dragged towards this side because of this battery. And when the charge carriers move away from the junction, this junction, they carry heat energy along with them. So because of that, carrying heat energy from the charge carriers, as long as there is a supply of electric potential in this circuit, so that phenomenon continues, and because of that, this side becomes cold junction and this side becomes hot junction. So to avoid overheating of this junction, people use some heat sinks. In fact, in both cases, people use heat sinks. For simplicity, I have not drawn the heat sinks over here. So this is the concept of thermoelectric cooler. It is slightly different concept than the thermoelectric generator. So by using these devices, we can do a lot of things, especially for the pollution-free future of this world. As an example, we can see here the most of the energy that we produce for our need is getting lost as an waste heat. So only about 35% energy is useful, and remaining 65% is getting in the form of waste waste heat. And thermoelectric generators can be one of the solutions which can use this kind of waste heat to convert that waste heat into electrical power. So we know there are many sites, many reasons, many places where we can find waste heat, and just by mounting those thermoelectric generators on the places where we find waste heat, we can extract that waste heat and we can produce some electrical power, and that can be useful for any other applications that can help us to minimize the use of the pollutant or any oil related fuels. So they are very useful in generating electrical power from industrial and automobile waste heat. That is the one important applications. So this is a kind of demonstration that people have shown experimentally, that by fixing thermoelectric generators on exhaust pipe of the automobiles. This is an exhaust pipe, and usually exhaust pipes will be having very high temperature because of that exhaust gas. So typically 400 to 500 degrees Celsius temperature one can find. So that kind of waste heat can be extracted from the thermoelectric generator, and they demonstrated about 1 kilowatt electrical power production from a device of thermoelectric generator. So this is possible, but still it is under research level. Still it is not implemented commercially in successfully. So there are different reasons, mainly associated with efficiency and all. So that's why people are working towards that aspect. So once that is solved, then we can use the thermoelectric generators everywhere, wherever we find the waste heat. And you can also find in market, you can find a stove and coupled with a small thermoelectric generator. So this stove, the heat of this stove can be used by this thermoelectric generator, small thermoelectric generator, and that can be used for your mobile charging or other energy electrical power need applications um, wherever possible. So particularly when you are in remote area, so you can use such kind of devices to use for your need. And this is the one of the important applications of the thermoelectric generators. Uh, they are presently being used as power sources in space missions. So as we know, the design of thermoelectric generator, it is just solid state construction. So because of that, they are quite suitable for extreme environment applications. That's why they are preferred in such space missions. So space mission means it is a kind of very extreme environmental condition. So in such extreme situations, these devices can work successfully because of their construction, solid state construction. And the reliability of thermoelectric generators makes them a great solution for places which are too far or too expensive or too dangerous for a repair or maintenance. So they use typically they work successfully because there is no complex science behind that thermoelectric device. It is just two types of thermoelectric conductors connected in series, and it is just a solid state device. There is no a complex circuit or complex electronics involved in that device. That's why because of that simplicity, people prefer in such applications where we don't have to worry about the repair or maintenance because that is not possible once the satellites or space missions are sent into deep space. So here, this is an example of, this is an image of radioisotope thermoelectric generator. In space missions, particularly radioisotope thermoelectric generators are used. So this is a thermoelectric generator where the heat source or thermal source is a radioisotope. So radioisotope will be kept inside this hot block, and by controlled reaction of radioisotope, they can produce a constant heat generation from the radioisotope. And along the wall of this hot block, on the surface of this hot block, they attach all the thermoelectric generators or the PN junctions directly on the wall of this hot block. And because of that, the hot block, the contact of hot block between the surface and the devices act as a hot side of the device, and the outer side will act as a cold side of the device. And by using such configuration, they can able to get sufficient electric power to run space missions. So this is quite successful, and once they are fabricated, they work successfully even more than 10 years without any problems. So that is all because of the solid state and simple concept of these devices. So these thermoelectric generators can also be used to convert solar thermal energy into electric power, or that electrical power produced can also be used to produce hydrogen. So hydrogen is a new fuel, a very clean fuel, which is preferred by different countries in order to minimize the air pollution that is happening because of the crude oil use. So here, again, the concept is very simple. We have this device, and we need to have some temperature gradient along the or across the device, and this temperature gradient can be created by just by solar radiation. But directly using solar light will not produce enough temperature gradient across the device, and because of that, one can use concentrators or lens, and by using lens, we can focus the solar radiation into high density light, so that can produce more heating effect on the hot side, on the top surface of the device, and because of that we can achieve better temperature gradient. So this surface works as a hot side and this as a cold side, and one can get electrical potential. And this electrical potential can be given to water splitting units where hydrogen can be produced. So by immersing just 2 electrodes in water bath with some salt, so one can able to produce hydrogen without any problems. But only thing is we need electrical potential or electrical energy, DC current. So uh, that can be achieved by this concept. So these thermoelectric generators uh, nowadays are also uh, getting attention by the research community to use them for to power sensors and electronics. So particularly this research is going on, that is wearable um, thermoelectric generators for human body heat harvesting. So by having a flexible thermoelectric devices, one can extract the human body heat to convert that into electrical potential. So as you can see in this figure, this is a small thermoelectric generator mounted on the human body, and it can produce about 2.9 or 3 millivolts of electric potential. So this is a small voltage. This is just a small test generator uh, they have tested over here. It is a small voltage, uh, and this device can be able to produce just microwatt or milliwatt kind of power outputs. But this kind of micro or milliwatt can be sufficient to these kind of applications. So for example, wireless sensor networks, where those small sensors will require very small amount of energy, electrical energy, to run. So in such cases, even in devices where data transfer takes place, we can use this kind of small power. And particularly these three are uh, really interesting, where people are working towards body heat powered medical sensors and wrist watches, flashlights. So different applications are possible by using such uh, uh, energy harvesting devices, particularly human body waste energy harvesting devices. Even though they are producing very small power, but that small power is sufficient to run sensors or small electronic devices. So that is very useful without being using any kind of electrical energy source. One can achieve uh, the the energy production by using thermoelectric generators, and that too with just body heat or any normal waste heat available around. So coming to the thermoelectric coolers are also very useful in different areas. Particularly, they are popular in laser equipments because they can work as a cooling device for the laser diodes. So that's why people prefer. They can effectively cool this small specific area when on which they are fixed. So that's why people use in the laser equipment devices. Today there are portable coolers, mini refrigerators. As you can see here, this is a thermoelectric cool bag. You can use this as a journey bag. Alongside, it works as a cooler. So you can put your things uh, which are need to be maintained under low temperature. And they are useful in cooling electronic components, and for small instruments where the cooling is required. In such cases also they can be used. And in case of medical and laboratory sample cooling and even climate control jackets, still research is going on. So where jackets can be used uh, as a comfortable jackets, uh, in different weather conditions. So if outside is extremely cold weather, you can convert that jacket into hot jacket or warm jacket. If outside weather is very hot, harsh, then you can convert that into a cool jacket. So by using Peltier effect or thermoelectric coolers, which are fixed on the jackets. So there are different applications of thermoelectric coolers. Even there are some car companies which are using these thermoelectric heating or cooling system on the car seats. So instead of cooling entire car, so we can cool only the car seats. So that can give comfortness to uh, the people who use the vehicle. Alongside, it can save energy instead of cooling entire car. So if one can use that kind of concept, that can be useful, but still they are not commercially available now. So for all these applications, we need to make those devices, we need suitable material. So based on thermoelectric concept of thermoelectric generator, these materials are thermoelectric materials, and we know we can define logically what are the requirements of these materials. So materials should produce more voltage under a given temperature gradient. Means when we apply temperature gradient, the material should produce sufficient voltage. So that kind of materials we need to effectively convert heat gradient into voltage, and charges should flow very easily. So again, when we maintain temperature gradients, charges should flow from hot side to cold side. If charges suffer, or if we take any insulator, the moment of charges is very difficult. Even you apply temperature, even after the application of temperature gradient. So we need materials or conductors in which charges can flow easily. And another requirement is heat flow should be minimum from hot side to cold side. That means when we apply the thermal source on one side, the other side should be always like at lower temperature as compared to this side. So if this side temperature becomes this side temperature, then there is no temperature gradient across the device. When there is no temperature gradient across the device, then there is no voltage production from the devices. So materials which uh, control the heat flow from hot side to cold side are important for this kind of applications. So what these points mean is we need large Seebeck coefficient, that is already as we defined delta V by delta T, large S, and we need better conductivity, electrical conductivity, but we need at the same time we need very low thermal conductivity. In fact, this is very clear from the standard expression of thermoelectric efficiency that is defined as ZT. It is given by S square sigma divided by K into T, where T is the temperature, average temperature of the device. So S square, S is Seebeck coefficient, sigma is electrical conductivity, K is thermal conductivity. So S and sigma are in the numerator, so which can be clearly seen here. We need better values of S and sigma, so they are in the numerator, and K is in the denominator. So that's why we must need low K value to have better ZT value. So better ZT value means better efficiency of the devices, and materials which have better ZT value are suitable for the thermoelectric applications. And we have two types of conductors, well-known conductors. One is metals and another is semiconductors. And the basic properties of these materials are like this. Seebeck coefficient in case of metals is very small, and electrical conductivity, we know it is very high in case of metals, and also thermal conductivity is also very high. When we look semiconductors, the Seebeck coefficient is very high or high, but electrical conductivity is not that high, but it is moderate, and but it can be tuned, so that is very important. And the thermal conductivity is very low or moderate, so low to moderate. So comparing these two conductors, we can see semiconductors are far better than metals. So metals are suitable only in this point, and they have good electrical conductivity. But remaining two factors, which are S and K, they are negative points. So that's why metals are not suitable. In fact, even though very small thermoelectric voltage, uh, um, they are having a very small thermoelectric power or Seebeck coefficient, that is not that will not affect much to the device. But this aspect of having very high thermal conductivity makes devices perform very poorly, because we cannot achieve temperature gradients if we use metals as thermoelectric materials. So if this is a metal, then we are going to heat this side, and this heat will easily flow from hot side to cold side. Here also, if it is metal, it easily flows from hot side to cold side. Then we don't have any temperature gradient across the device. So when we don't have any temperature gradient, there is no diffusion of charge carriers from net diffusion of charge carriers from one direction to another direction, and because of that, there is no production of voltage. So that's why semiconductors having a moderate properties are quite suitable for these applications. That's why people use um, mostly semiconductors to prepare these devices, particularly N-type semiconductor on one side, P-type semiconductor on the other side. But only thing is, some semiconductors have high thermal conductivity, and one has to avoid such semiconductors and use semiconductors which are having a very low thermal conductivity. Then only one can achieve a sufficient temperature gradient across the device. So the challenges, there are mainly two challenges. One is very low conversion efficiency, as you can see from this figure. So this is thermoelectric device efficiency for different temperature gradient applied to the device. Gradient means the temperature of hot side minus temperature of cold side, that is the gradient. So under different temperature gradient, we can see there is a different efficiency from the devices. So presently we have one commercial devices which are working with ZT 1 to 2. So these curves indicate they are for different ZT values. So for if materials, thermoelectric materials having ZT equal to 1, we have this kind of efficiency. If we use ZT is equal to 2, this is the efficiency of the device. For 3, this is the efficiency. 5, this is the efficiency. So presently we have roughly 1 to 2, and by applying 200 degrees of temperature reference across the device, we can see we produce about 10 to 12% efficiency. Of course, at high temperature it is more, but typically we can able to produce from different sources up to 200 degrees Celsius temperature difference. So it is very small temperature efficiency of these devices that makes them non-popular for different reasons. For effective conversion of heat into electric power, they are not that efficient. So, but if one can use improve the ZT values of these materials, one can achieve better efficiency. But still, people are working. Of course, 3 is recently reported, but the commercial devices with ZT equal to 3 are not yet realized. So ZT should be improved in order to improve efficiency of devices. That is the one main challenge. And another challenge is the unavailability of the best performing non-toxic material to make devices. Presently, what we use is bismuth telluride and lead telluride. So all the commercial devices are made from these kind of materials, but these materials are quite expensive and toxic. So for example, you can see they are scarce also. So the abundance is very low. For example, tellurium and bismuth, they are very rare on the earth crust. So that is one big concern. Especially tellurium is very scarce. It is less it is less available than gold. So that is a big problem. So research is going on to find less expensive and less toxic materials on this aspect. So low conversion efficiency and abundant materials, unavailability of abundant materials are the two major problems in the field or in the technology. So there are different ways to enhance efficiency. People use nanoscale approach, composite formation, impurity atom doping, heavy element compounds, design of alloys. So each of these require enough time to explain properly, but in this talk, I will be covering briefly about nanoscale approach. Since this webinar is about nanomaterials, so I will be focusing on this concept, how nanoscale approach can improve the efficiency of thermoelectric materials. So the nanomaterials, mainly the two popular things in nanomaterials are, particularly in thermoelectric technology, are thin films and nanowires. Quantum dots are also important, but you cannot use single quantum dot for any applications. But at the same time, thin film can be used independently. Nanowires can be presently. There are techniques to use such very fine nanowires to construct devices. So there is a possibility of using thin films and nanowires in thermoelectrics. So that's why they are gaining popularity. So what happens in case of thin films and nanowires? They are 2D and 1D materials. So in thin films and nanowires, electrons are confined to move along the longitudinal direction, along the length of the thin film, or along the length of the nanowire. So it is a confined movement of the electrons. So, but in that direction, they can move without being scattered. Only thing is they can't move in the transverse direction, but they can easily move without being scattered along the length of the films or nanowires. Or they can move in 2D and 1D direction in case of thin film and nanowires respectively. And so this means we can retain the electrical conductivity in case of thin films and nanowires. So we are not losing electrical conductivity even after going there. So there will be small decrease, but it is not much. But in case of phonons are not confined exactly like how electrons are confined. So phonons may scatter off the surface, and this will reduce the thermal conductivity. So phonons can be scattered off from the surface of the nanowires because of very narrow thickness of the nanowires as well as very small thickness of the thin films. From the surface itself, a significant amount of phonons can be scattered. So once phonons are scattered more, then there is a significant reduction in the thermal conductivity. Particularly, it is lattice thermal conductivity. So by this approach, we can achieve very low thermal conductivity. That is very important aspect. And another important aspect is, as we have seen in our previous lecture, the density of states are going to be modified when we go from bulk to nanostructures. And if we consider quantum well, or this is thin film and quantum wire, the density of states is entirely different as compared to the normal one, bulk one. So here we can see a drastic change of density of states with respect to energy. Here also drastic change of density of states with respect to energy. But whereas there is a smooth change in density of states with respect to energy in case of bulk semiconductor. By having this kind of drastic changes in the density of states, we can improve Seebeck coefficient. So by going from bulk to thin film or nanowires, we can see changes in the Seebeck coefficient. Seebeck coefficient is also defined as this with this expression where it has a relation with the derivative of conductivity, energy dependent conductivity. But that energy dependent conductivity, this conductivity is Ne mu. So N of E is energy dependent concentration, that is nothing but density of states. So by tuning density of sets, we are tuning sigma, and the drastic change means drastic value of this parameter. So it is the derivative of a derivative with respect to energy, means with respect to energy, if there is a much large change, then this value will be more. So that's why Seebeck coefficient will be more. But in case of bulk, it is a smooth change, so not much change. If you consider here, it is just flat, so it is constant, almost very negligible change. So whenever we have derivative term, so if change is much in the parameter, then we get a large value from that term. So Seebeck coefficients can be effectively improved by decreasing the dimension from bulk to thin films and nanowires. Of course, quantum dots also one can achieve improvements, but they are not practically useful because single quantum dots we can't use for the application. But for the study purpose, one can study using very high and techniques, but they are not suitable. But nanowires and thin films are quite suitable, but nanowires, again, they are difficult to handle. So, but efficiency wise, we can see the improvements. So there are two improvements, simultaneous improvements. We can see improvements in S, and we can also see improvement reduction in K. So two parameters are taken care of in the ZT value. So that's why we can see improvement in the ZT value, overall ZT value or efficiency of the materials. So these are some theoretical predictions that researchers reported on thin films and nanowires. You can see this is bulk, dotted line is bulk. But once it is thin film, having this kind of thickness, so you can see 20 angstrom, 40 angstrom means 4 nanometer, 2 nanometer. By reducing the thickness of the thin films, you can see the how much efficiency they have predicted. So one can reach even 6 ZT of 6. Presently we are working with the ZT 1 to 2, but by going into thin films, but very narrow thin films, 2 nanometer, less than 2 nanometer means they are very narrow thin films. So one can achieve very high ZT value. Similarly, the Seebeck coefficient improvement has been predicted theoretically when the dimension of nanowires is decreased. You can see at 200 angstrom thickness, means around 20 nanometer thickness of the nanowires. The Seebeck coefficient, this is normalized Seebeck coefficient, so it is here. But as we reduce the dimension, we can achieve very high Seebeck coefficient. So that is almost like 1.3, more than 1.3 times more value, large value than this value. So Seebeck coefficient can be improved in the nanowires, as well as ZT value can also be improved both in thin films as well as in the nanowires. So these are the just the initial theoretical works which help us to understand the concept of enhancement in thermoelectric ZT. Experimentally, in 2001, Venkat Subramanian reported a very high ZT value from a thin film. It was bismuth telluride and lead antimony telluride superlattice thin film, where they produce about 2.5 ZT value even in the year 2001 itself. So, but that thin film was very, very fine, very, very thin, and requires a special technique to fabricate such superlattice thin films. But the fact is, the enhancement in ZT value is possible with such thin films. So very simple approach in nanomaterials is this one. So they are known as nanostructured bulk materials. And for this approach, so we don't have to use any special techniques. So by simple synthesis methods, one can achieve this kind of materials. So typically what we see bulk materials, they can be broken into pieces, and possibly nano range particles. Then they are again pressed into bulk material, and by doing this kind of the process, we can now have the bulk material. Again, it is a bulk material, but it is a nanostructured bulk material. So in this material, we can significantly reduce the thermal conductivity. In case of bulk phonons, because of the crystalline nature of entire crystalline nature of the material, phonons can flow very easily from one side to another side, or heat can flow from one side to another side, because phonons are moving very smoothly without being scattered much. But in case of this kind of structure, we have a lot of interfaces in the material, and due to that, the phonons can be scattered on all the interfaces, using all the interfaces, and then the heat flow can be minimized. So by using this kind of simple technique, we can suppress the flow of phonons, and we can achieve low thermal conductivity, and without much affecting the electrical properties like electrical conductivity and Seebeck coefficient. In fact, Seebeck coefficient can be improved in such materials because of these interfaces and some nanoscale structures in the material. Quantum confinement effects still exist, but very dilute in nature. But because of that, a small improvement in the Seebeck coefficient can be observed in case of nanostructured bulk materials. So here also a small improvement in Seebeck coefficient, but a significant reduction in thermal conductivity can be achieved in these kind of materials. So this approach is very simple as compared to the thin film or nanowires, even though the in thin films and nanowires enhancement is very high, but in practical, the preparation methods are very difficult. You need to prepare thin films and nanowires of in the range of 1 to 2 nanometer, 1 to less than 10 nanometers. So that is quite a limiting factor to make commercial devices. So that's why even after reporting such high values in thin films and nanowires, they are not yet realized in day-to-day life. But this is a kind of a promising approach, because they can be easily prepared, and devices can be made in a low cost. And in fact, we are working on this nanostructured bulk materials. In fact, we are not exactly preparing nanomaterials. They are in a few hundred nanometer in size, our particles, but still it is not a kind of standard bulk material. It is nanostructured or microstructured bulk material, and from this material we can expect very low thermal conductivity, but maintaining other parameters like good electrical conductivity and good Seebeck coefficient. So this is a very simple approach of preparing copper sulfide, which was reported by our group during my PhD when I was working with Professor M.K. Rebinal. So this is the preparation of copper sulfide by ultrasonication method using sulfur solution and copper plate. And because of ultrasonication, we get sufficient amount of copper sulfide by such simple reactions. And copper sulfide is very promising semiconductor for the thermoelectric applications, and getting very attention from the research community because of this abundance of copper and sulfur elements like copper and sulfur and its good electrical nature. And we are also working towards the same material, but we are trying to develop low cost material synthesis methods for such materials, so that those materials can be used to prepare thermoelectric devices in a low cost. So today, if we see the scenario till 1970 or 1980s, even up to 2000, the maximum Zt value of all the thermoelectric materials was 1 or around 1. And because of this nanostructured approach, so these are all bulk materials. And after the concept of nanostructured materials, people have reported very high value, as compared to their bulk counterpart. So now we are having nearly more than 2 ZT value in case of nanostructured materials. This scale is up to 2010. In 2020, we have almost like 3 kind of ZT value in case of nanostructured materials. So there is a positive growth in the technology, and if we achieve more than 3 or 4 kind of ZT value, and this technology can be useful to recover waste heat and to convert that into electrical power or to generate hydrogen, etc. So I'd like to conclude with a few positive comments or remarks about these thermoelectric generators. These thermoelectric generators have no moving parts. As you have seen already, it is just a physical device. There are no moving parts, and therefore they are virtually maintenance free. So you don't have to maintain them. So once they are prepared, once they are fabricated, they can work as long as you use, and they can have a long lifetime. They are highly reliable, again, because of solid state construction, and they do not release any toxic gas during use. So that is very important uh, uh, as far as environment is concerned. And they can work in aerospace. Already we have seen an example of the radioisotope thermoelectric generator. Because of the solid state construction of the devices, they can work in zero gravity or any orientation, so that makes them suitable for aerospace applications. And in remote areas where there are no conventional energy sources available, in such cases these devices can be very useful for emergency purpose or some small power generation applications. These devices can be used. And most importantly, the waste heat recovery can be done very effectively with such simple devices. And utilizing waste heat into useful electrical power can help a lot to improve the energy consumption scenario. With that, I would like to thank my university here, Swansea University, and Wells government for giving me an opportunity to work as a researcher in the campus. I would like to thank my supervisor, Dr. Charlie Daniel of the Swansea University, and also I would like to thank my PhD supervisor, Professor M.K. Rabinal, Karnataka Institute, Dharwad, for their guidance and support. Finally, I would like to thank the organizers of BLDEA associations, SB Arts and KCP Science College, Vijayapur, for giving me an opportunity to present a small talk on thermoelectric effects. Thank you. Thank you very much.
So the questions are being posted in the chat box. So please go through them.
Yeah, I will. Just a minute. So one question is, how can we get more ZT values? Is there any method? As I have spoken about this, we can improve ZT values by different approaches. Like I can show you some. Sorry. As I mentioned, couple of the methods how people can improve the ZT values. So these are the different approaches by which we can enhance the ZT value. So just I have explained only one type of approach, that is nanoscale approach. Ultimately, it is about ZT. So here we have S square sigma divided by K. So we need to improve S, and we need to improve sigma, and we need to decrease K. So that is all is about in improving ZT. But the tuning of these parameters, independent tuning of these parameters, is very difficult because all are electronic parameter and all are coupled together very strongly to each other. If you tune one of the parameters, other will be affected. So it is difficult to tune the properties. For example, the simplest example is we need more sigma, means more electrical conductivity. So if we want more sigma, means we are increasing more K. So that means we are going towards metals. So it is a bit difficult. One has to optimize such that for a particular carrier concentration, they can achieve a moderate electrical conductivity and a moderate Seebeck coefficient and very low thermal conductivity. So getting very high electrical conductivity is also not suitable. Getting very high Seebeck coefficient is also not suitable for the applications. A moderate aspect, a moderate tuning or optimization is necessary to have a better ZT value from these materials. So that can be done by using different methods. For example, if we have very low thermal electrical conductivity from a semiconductor, in that case, if we want to improve sigma, then you can dope that material. For example, if you dope silicon with p-type or n-type material, you can tune the electrical conductivity, you can improve its Seebeck coefficient. So different methods are there. So doping or impurity, adding impurity, or making composites. By making composites, you can reduce thermal conductivity. So because of scattering of phonons in the composites, you can significantly reduce K. By doping, you can tune sigma as well as S. Of course, it also affects K, but it is not much. But mainly sigma will be affected by doping. Similarly, by nanostructures, you can significantly improve S as well as you can significantly decrease K, and because of that, you get better value of ZT. Another question from Wadiraj is there any alternative ways instead of placing thermoelectric elements in series within generator modules to get voltage output levels in the range required by digital electronic devices? So in series, when we put in series, that depends on how much potential we need and how much temperature gradient we are applying to the device. So if you use only one junction and apply more temperature gradient, then you can also get sufficient voltage from single junction. So in such cases, you need to have very long conductors that is not suitable for practical applications. So that's why people try to make as small as possible devices, as small as possible. Because of that, people prefer to use multiple junctions, so that with a thin device and small temperature gradient can create sufficient voltage that can be used to power a small electronic devices. How to evaluate ZT from Tanjavur Govindraj. ZT evaluation, again, you need to measure Seebeck coefficient and measure electrical conductivity and measure thermal conductivity of a material and put into this value, this formula. So Seebeck coefficient can be measured by applying temperature gradient and measuring the voltage production. So then that is delta V by delta T. If you take delta V by delta T, that is nothing but Seebeck coefficient. And you have well-known methods for electrical conductivity measurement. You have 2-probe method, 4-probe method. You can use any one of methods to measure electrical conductivity of these materials. Thermal conductivity is a bit difficult, but still there are steady state methods where you can apply some standard methods like laser heating method or laser laser diffusion method, or by measuring specific heat, indirectly you can measure the thermal conductivity, or a steady state method where you can heat one side of the conductor and measure the temperature gradient achieved along the conductor. And if you know standard formula for K, it is about the heat flow and length, how much length you use, how much temperature gradient is achieved, what is the cross sectional area of the material used. All those parameters are required to estimate K. So once you put all the parameters in the formula of K, you can get the thermal conductivity value. So once you measure all these three parameters and what is the temperature you are working with the material, if you substitute that value here, you will get ZT value. Yeah. Most of them are just thank you. One is good afternoon. Sorry. Another question is from Anirudh Kulkarni. When we was work during automobile exhaust waste heat recovery system, cold side temperature of thermometer generator 60 to 70 degree, unable to maintain cold side temperature by using water jacket, heat pipe, any other method. Yeah, this is the actually practical problem that is associated with thermometer technology. People are working with finding better heat sinks. That itself is a research now, because in these devices we must have some heat sinks here. Uh, so when we heat this side, heat is ultimately flowing slowly from this side to this side. Even though they are semiconductors, still they able to carry, they able to allow heat from hot side to cold side. And initially you will be having sufficient temperature gradient, but after some time you will be having increase in temperature of the cold side, and that is very big limitation of this technology. In fact, people are working to have different heat sink designs, again nanostructured heat sinks where surface area is very high, and such devices, such heat sinks, if one can mount on the cold side, and by water flowing on that sinks, because of more surface area of the heat sinks, they can be effectively remove the the heat from the cold side. But still it is not at a kind of commercially realized concepts. So people are working to make better heat sinks so that a better temperature gradient is always maintained for long duration. But in fact, presently in commercial devices, people use either cold water flow along with sink. So that is in fact working effectively. But as I say, it is 60 to 70 degree means this commercially what people in industrial, what people are working is they are working with at high temperature like 400 500 degrees Celsius heating, and because of that they ultimately get some temperature gradient across the devices when they use some heat sinks. But when you use these devices around room temperature, the temperature gradient is not much. And even after using the heat sinks, you cannot get a sufficient delta T, because hot side's temperature itself is not enough to get better delta T. So yeah, that is the limitation of this technology, and still people are working towards that. Yeah, I hope that is. Another question from Anirudh is it possible to generate cooling effect or thermometric cooler by using solar energy? Yeah, quite tricky. Like, you are using solar energy as a heat source, then that device will work as a generator, not as a cooler. But to convey you, you can generate that electric power and give that electrical power to another device which can be used as a thermoelectric cooler. Of course, it is not efficient method, but in case if you want, you can generate electrical power from one device and apply that electrical power to another one to make it as a thermoelectric cooler. So what is the range of Sanjay? What is the range of voltage generation? It will be, if you take one junction, it will be like few millivolts. But if you take one device, commercial device, it will produce about 1.5 volts, roughly 1.5 to 2 volts. And if you use multiple devices, such devices, you can produce 5 volt, 10 volts. Any voltage can be possible, depending on how many devices you are connecting in series. Can it's also, again, another question, possible in alloy metal? Yes, of course, alloys are very important materials for thermoelectric devices, where people found very low thermal conductivity by mixing 2 to 3 elements. Instead of using single element, by mixing 2 to 3 elements, they can able to produce very low thermal conducting materials with good electrical properties. So yeah, they are quite important materials for the applications. In fact, I couldn't able to cover all the factors because that needs more time. So that's why I covered only nanostructured based materials in this talk. Yeah, I think I covered all the questions. Thank you again. If there are any more questions, you can ask from your side. Madam, please.
Thank you, sir. Thank you for such a wonderful session. It's very helpful, sir. So,
thank you.
Now it's time to conclude this international webinar. I request Professor Srimati R.D. Joshi ma'am to propose the vote of thanks. Please, ma'am.
Good afternoon, everyone. Myself, Professor R.D. Joshi, Department of Computer Science, SB Arts and KCP Science College, Vijayapur. I feel honored to propose vote of thanks on behalf of Principal, Vice Principals, and Organizing Committee of BLDEA Associations, SB Arts and KCP Science College, Vijayapur. Firstly, I would like to thank our resource person of first session, Dr. C.H. Bosle sir, Professor, Department of Physics, Sanjay Godawat University, Attigere, Kolhapur. Thank you, sir, for your wonderful session. Now, I would like to thank our resource person of second session, Dr. Rajashri M. Hadlur Madam, Assistant Professor, Department of Physics, KLE Technological University, Hubli. Thank you, ma'am. I would like to thank our another resource person of third session, Dr. Rafiq Mullah sir, postdoctoral researcher, Energy Safety Research Institute, Swansea University, UK. Thank you, sir. I would like to thank our honorable principal, Dr. A.S. Pujar sir, for his encouragement and support for this function. Thank you, sir. I would like to thank our vice principals, Dr. U.S. Pujari sir and Professor G.R. Ambli sir. Thank you, sir. And also like to thank our NAC coordinator, Srimati Vidya Patil madam. Thank you, madam. I would like to thank HOD, Department of Physics, Professor C.N. Chowgle. Thank you, sir. A special thanks to the advisory committee members, Professor N.H. Ayachit, Registrar, KLE Technological University, Hubli. Thank you, sir. Dr. S.M. Shivaprasad, ICMS, JNCASR, Bangalore, Director, KSHEA, Dharwad. Thank you, sir. Professor M.K. Rabinal, sir, Department of Physics, Rani Channamma University, Belgavi. Thank you, sir. Professor B.J. Hegde, sir, Chairman, Department of Physics, Rani Channamma University, Belgavi. Thank you, sir. I would like to thank Dr. Girija Nimbal, Coordinator, Department of PG Students in Physics. Thank you, madam. I would like to thank Professor Pavan Kumar Mahindkar and Professor S.V. Ambase, sir, for their technical support to this webinar. Thank you, sir. Thank you, one and all.
Okay. So feedback link will be sent in the has been sent in the YouTube live chat box. You can check it. Thank you one and all.